Che succede? Ok, si è rotto. Ragazzi. Ok. Non ho capito cosa era successo. Oh no, tutti i miei meme. Boh, basta spoiler. Vuoi provare Greta? Ok.
Vado a prendere.
Wow. Aspetta, e vedrai il keynote fatto da una che si è svegliata alle 4 e mezza ed è totalmente rimbambita.
Niente polizia, niente gente che veniva a buttare la roba così basta, si buttano giù la camera.
Ottimo.
Bellissimo proprio. Spettacolo.
Solo quando sono svegliata ero un po' male, sono svegliata male proprio. Ah.
No dai, no dai.
Perché stai facendo? Guarda, aiuto, Adam. Ma perché hai fatto così?
Sì, penso sia il cavo.
No, è morto. Qua va, ma lì. Ma pare che tornava.
Puoi mandarmi la presentazione? È sul bene il tuo posto. Dai. Fammi vedere se funziona di nuovo il mio. Adesso che fai. Oh no, aspetta, questo era tuo.
Oh,
No, no,
no.
questo era mio.
Sì, sì.
Ok, scusa, stavo qua. Certo, svegliarsi alle 4 e mezza. No, Budo. No, Budo. Ok, tu fai.
Tu hai PowerPoint?
Oh my god, no. Ok, devi trovare un altro computer.
Aspetta, ma tu te... Ah, aspetta, ho un'idea. Mi
Guarda,
presti il
sì,
dongle?
sì, sì. Aspetta. Sì, funziona.
Ok. E anche se vado così... Wow.
To the 10th edition of Numerical and Symbolic Abstract Domain Workshop. I'm Vincenzo Arcieri, and I'm super happy to have organized the NSAD workshop with Michele Pasqua there. And this workshop was missing since 4 years. The last edition was in 2020, and me and Michele are super happy to revive NSAD this year. So we got 6 papers, 5 full papers and 1 short paper, and yeah, we feature a keynote speaker by Caterina Urban, and we will start with her, with the second part, the part 2 of the talk that she had in SAS. And so that's all. I leave the floor to Caterina with her talk. Thank you.
Okay, good. Okay, thanks to the organizer for the invitation. So yes, this is sort of a part 2. So I did a tutorial at SAS on machine learning verification. And here I decided to actually remove the word verification. I will not just talk about verification, but various things where we can basically use abstract domains for machine learning in various ways. Why I started caring about machine learning is mainly, well, because as you know, there's a lot of machine learning being used these days, and a lot of it also is appearing more and more and being used more and more in high-stakes systems. High-stakes is safety critical, but also systems or situations where this kind of software has an impact, I would say, on our socio-economic lives. And there are various reasons for this. So first of all, we can now use machine learning to do things that we couldn't do with explicit programming. You think, well, self-driving cars, image-based taxiing, takeoff and landing. Yeah, they are looking at these things in the avionics sector. We can also use machine learning as surrogate models. This was basically what I was looking at in the tutorial. We have reference systems, and we can use machine learning to approximate these systems. And this allows us to basically equip airplanes, for instance, with new functionalities that we didn't have before. And then finally, this socioeconomic impact comes where we can use machine learning to automate decisions in healthcare, finance, hiring, and what's not. So I just talk about machine learning system, machine learning software. For me, in fact, the machine learning software is anywhere that appears in the machine learning development pipeline. So any code that is used for preparing data, for training data, for, well, actually, doing the predictions. So the talk afterwards will talk about this data preparation phase, actually. So that works well because I'm talking mainly about these 2 parts. I will start with the model deployment phase. Touch a bit on training, and the rest, well, Greta will continue afterwards. So it all works out. So I'm starting with the model deployment, and here the main challenge here, so these are the models that are already trained, okay? And the main challenge from a formal methods, formal guarantees point of view is that these are trained optimizing some loss function. So you basically have some probabilistic guarantees, right, on their behavior, but it doesn't give you any formal guarantees on their behavior under all circumstances. So this is where problems come from. In particular, in the machine learning community, this started, but they noticed basically that, I mean, you all know this, that these models are vulnerable to small perturbation of their input that can dramatically change their outcome. And this is actually also the motivation why the formal methods community started looking at this kind of systems. So historically, the formal methods community has worked on traditionally safety critical software. And in the past, I don't know, I would say 10 years or so, we have been looking more and more at machine learning software. So out of curiosity, I looked at the publications on Google Scholar. I took some keywords that are common in the field. And these are, you see the number of papers. So 2024 is not yet finished, but we already have a lot of papers in the pipeline. So this is for us, the formal methods community. But the interest and reaction from the machine learning community is not there. They really do not care about any of this, pretty much. I started asking myself if there is any way to make formal methods interesting or have a dialogue with the machine learning community in some way. And so this keynote basically will cover 3 ways or 3 possible directions in which we can do that. In the first direction, I will stay on verification, so closer to what we are used to. And then I will go a bit further, so into the training, so directly doing machine learning stuff with a touch of formal methods, and then something in between where we can use formal methods to do something else than verification, which is explainability. And what one thing I didn't say, please, we're a small workshop, ask questions at any point, you don't need to wait until the end. Okay, so verification. So this was a nice collaboration with Fujitsu. They had a nice use case that they needed to solve. And this got me thinking into what kind of verification problems we can do that may be also somehow useful or interesting to the machine learning community to go beyond this local robustness problem that they look into. So essentially, what happened was, yes, most of the community now is doing this robustness verification. What happened to us in this project that we had to do robustness verification, but with a touch of awareness for interpretability concerns. I'll make this more clear, of course, but this is a bit the flavor. So it's not robustness of the classification, really, but it's robustness of the explanations for the classification, in essence. So the problem is this: we had what they had was basically a system that was classifying some metal pieces based on whether they were defective or not. So they had essentially the camera was looking at the pieces, and based on their aspect, they was deciding whether it was an okay piece or defective piece. And what happened was that often they had problems with the like regular perturbations of the light, so modifications in the light of the room. They had sometimes some dust that was covering the objective, so there was what we call patch placement. So basically some part of the image was a bit covered, and sometimes the object was not exactly in the position where they were expecting it. It was just slightly shifted left or right and things like that. So we had some sort of what we call semantic perturbations. And so the idea was identifying safe ranges for the parameters of this perturbation. So when can we trust the classification of the system in case of this perturbation that can happen naturally in this context? And what we realized was that, in fact, if we just look at the classification robustness, this was not enough. We had cases where, I mean, this is with an MNIST image, but we had cases with these metal pieces where just completely changing just the brightness of the image, we couldn't see the metal piece anymore, but it was still classified as an okay piece. So the classification didn't mean anything, in essence. So what got us thinking was that, well, maybe we can have something more meaningful that we can look at that will be a bit more semantically meaningful in terms of robustness. So what we looked at was in the machine learning community, they have a lot of these explainability techniques or ways to explain why some image is classified in some ways. And one of them, I mean, there are more advanced techniques these days, but one of them that has been used a lot are all these gradient-based techniques, where basically you have your image, and based on the magnitude of the gradients, the classification with respect to the inputs, you basically identify the pixels that are more responsible in a way for the classification. So we decided to do that as well with our images. So here it is our 8 image where we just increase the brightness. And you see that at the beginning you can sort of distinguish the H shape, but beyond a certain point, you don't really see the H shape anymore because, well, the brightness of the image is too much in this, and you lose basically the reason for classifying it as an 8, even though the model still classifies as an 8. So there is a sort of, maybe around here. So here we can still sort of see an 8, here we don't see it anymore. So what we decided to do is basically use this criteria to define a new robustness problem, which was the robustness of the explanations, the saliency map. These are called saliency map or gradient-based explanations, however you want to call them. So we have, what we decided to do was basically say, okay, we have our image and the perturbations that we can apply to this image. So for each of these perturbations, we have a corresponding saliency map and this explanation. We can compute this gradient-based explanation. And then depending on the perturbations, so the brightness change, the patch placement or the translation of the image, we have some sort of expectation on what is the saliency map. So basically we have the original saliency map. We can also apply the transformations to that saliency map. And then we can compute the distance between those, the expected and the actual one that we get. And beyond a certain threshold, then maybe we don't trust. The distance is too much. And so we say that this is inconsistent and we cannot trust this classification anymore beyond this perturbation point. So we can allow this much perturbation of the brightness. Beyond that, we don't trust the model anymore. So I just wanted to give you a bit of a flavor of what kind of analysis we can do with that. And give you, so here, spoiler, there won't be any abstraction yet. So in fact, this is one place where we're missing abstraction still, and it's an opportunity for maybe doing some research in this direction. So I'll give you a small example. This is an image with 4 pixels that is classified as a dog or a cat. Bear with me. So the nodes, we have one single hidden layer with a ReLU activation function, so this max function between the linear combination of the nodes in the previous layer and 0. So this is our image, and you can obviously see that if you do all the calculations, this is obviously a cat. From this image, you can clearly see a cat. I hope nobody disagrees with me. Okay, never mind. So for the classification, with these 4 pixels, we get a cat. The saliency map, as I said, is basically the gradients of this node with respect to the input. So in essence, if you replace, you do the back substitution up to the input, you get the inputs with some coefficients. And these coefficients are basically the importance of the pixels with respect to the classification. So this is the saliency map for this image. So what it says basically is that this pixel here is the most important for deciding whether this is a cat or not. These two are somewhat less important, but equally important, and this is the least important pixel. So now if we do perturbation, we change the brightness of this image. This is the new image that we get. And this is the corresponding saliency map, or the corresponding explanation. So you see that the importance relationship is still somewhat maintained. This is still the least important pixel. This is still the most important one. These are slightly different, but still in between those two, in essence. If we go further, we do further perturbations. We get now that we don't distinguish the importance of these 2 pixels anymore, for instance. So here we are losing some relationships between the pixels, and the distance between them is increasing. So we can say, well, in this case, we can trust this much perturbation of the brightness, not beyond. So yeah, this is how we can say, okay, this is robust, beyond that is not. So how can we verify this robustness thing? So in the project, what we did, we actually leveraged this other work. Basically, it's a way to encode the perturbations directly as layers of the network. This way you basically end up with instead of having the image and considering all possible perturbations of the image, you basically have the parameters of your perturbation as input, and then the network basically encodes all possibilities of perturbation of the input image. So in the example, basically if we consider just brightness perturbations, this means we add the parameter to the network. We end up having the image as the bias values, basically of the nodes, and we add these edges. Okay, so then I have to check the time to not go too long on this, but okay. Okay, so then we end up with this network, and we basically want to find the ranges, or which range of this input space we can trust the classification or not. So we have this robustness of the explanation. So what we did was actually leverage the disactivation patterns of the ReLU. So the ReLU function is this piecewise linear function here. So in the whenever the input, the node is active, so it's is positive, this behaves as the identity function. So we say this is active, the ReLU is active. Whenever the input is negative, the ReLU is inactive, and so the value is 0. So in essence, you can consider it as a filter. Basically, it receives a signal, a value, 0, and it's active when the signal continues, as it is, inactive when the signal is killed and reset to 0. So I will use 1 to identify the active state of a ReLU, and 0 for the inactive state. So when I do the verification, okay, I will leverage these activation patterns to basically explore the input space. You'll see it's a very somewhat naive analysis for now, because there are no abstractions. So basically I start with my input image. So basically the parameter is 0, I have no perturbation. So the input image is my original image. And now I check what is the status with this input of my ReLUs. So in this case, they are all active. So that means that basically for all nodes, I pass the function as it is, or the value as it is. But in particular, what this pattern gives me is also constraints on the input space. So it's not just the single image, the original image that has this pattern, but other images in the same region of the input space. So in particular, when I say that all of these are active, this means that basically if I take their value, so their value is the linear combination of the nodes in the previous layer, this is always positive. Same for here, same here. Same for these nodes, right? These are the value of this node depends on the input plus the bias. This is all positive, greater or equal than 0, greater or equal than 0, all of them. When I put all of these constraints together, this basically identifies this region of the input space. So basically for all input parameters that have values between 0 and this 1/14th, they all share the same activation pattern. So basically I can do the analysis for this region of the input space, considering that all these ReLUs are always active. So we do classification robustness for now, and then I'll do the saliency map. So for the classification, this means that basically, okay, I start with this input space. They're all active, so I can do some sort of symbolic propagation. So I'm saying, okay, this is active, so it's the identity, so it remains the same. I do this linear transformation and so on. So this gives me basically expressions for these two nodes that depend on the input. And now what I want is a classification robustness. So what I want is that I always get a cut, so that this value is always greater than this value, which is here. And in this particular input space where I started the analysis, this is true. So here I have classification robustness. Okay, now let's do this saliency map robustness. So here, in essence, is the same, right? I can do the propagation as before. I do the backward propagation to get the gradients, leveraging still the activation patterns. For each activation pattern, since the ReLUs are fixed, basically it's the gradients are always constants, it's just coefficients. And in particular, the saliency map is really the same as the one of the original image. So the distance is 0, so we do have robustness there. Now, how do we explore the rest of the domain? We can do a naive search. So basically, we have our initial region of the input space. Here I have basically 2 parameters of perturbation, just to give you an idea on how we would do it. And then basically what we can try to do is basically find the adjacent activation patterns, and then see for each of them whether we have the robustness or not. So how we go about that? Well, we just flip the activation status of a ReLU. This will give us another region of the input space, this one here. And then this will give us other output constraints. We can do the same check there, and this is still robust for the classification. Similarly for the saliency map. Again, we have fixed all the ReLUs, so the saliency map is constant. The coefficients are constants. So we can just compute the distance with the original one, and this is below our threshold of distance 4. So we're all good. And then we can continue like this, right? We can flip and discover new parts of the input space until we cover the entire input space. So you see the difference between the classification robustness and the saliency map robustness. For the classification, we can trust perturbations of this brightness up to 0.5. But if we look at the stability or the robustness of these explanations, the saliency map, we can only go up to 0.25. So it's more strict. Then, of course, it depends on your distance, of course. Then you can imagine that this is just too much. You cannot do this on a larger scale network. There are just too many activation patterns to explore all of them. This was a rather small network, and we had just 2 input parameters, and we had all these many regions to explore. It was just not possible. So what we ended up doing in this work was do some sort of under approximation. So we did some search, what we called it geometric boundary search. So basically we were trying to go as far as possible from the original image. This is the original image, and these are the perturbations that we can apply to it. We try to go as far as possible from it until we find what we call the boundary. So here is the classification boundary, and here is the boundary of the saliency map, where the saliency map changes or it goes too far, basically. And of course, the white regions are regions that we have not explored. So we don't know if there are other regions here. It's just a very under-approximate, rough kind of exploration. But with some heuristics, we had basically, we could find things that looked reasonable, at least. So here we can, basically we go as far away as possible until we find the boundary, and then we try to explore the boundary around it. And then we can continue. Of course, we can go in other directions and keep exploring and so on. And this gives us an estimate, roughly. So we can say, well, definitely beyond this, we cannot go with brightness, and we cannot go beyond this with the patch opacity. Maybe there are stricter requirements, but beyond this, we are sure that we shouldn't go. And here we can say, okay, brightness, we can trust it up to roughly here. For the patch, it's kind of okay, possibly. We don't know what is there, but it's a bit like that. But even this, it actually doesn't really scale. I mean, I don't want to go into the details of the explanations or the experiments, but really we try different kind of combinations or different strategies for doing this this kind of analysis. And the summary of this, without going into the details, it doesn't scale beyond neurons, like 10,000 neurons and so on. So it's we need something else. So there are some opportunities here for this community. We need some abstractions for sure. So instead of doing this exact analysis, even if partial, right, we need to leverage abstractions. This way we can cover the entire input space, and we can do it faster. And then, on the other hand, we can also perhaps use this idea of robustness of explanations for other machine learning models. As just some ideas, if any of you wants to pick them up. Any questions so far? Yeah?
So you're talking about the semantic information, right?
Sorry.
Okay, so we're talking a lot about like one specific type of explanation,
Yeah.
right? Have you looked into any other like more abstract explanation, like for example, Lime, where they like make a linear representation?
Yeah. So no. This would be another option another way to go. Right?
Oh, okay.
This was one kind of explanation only. There are many others, and then yes, definitely you can try many others. There are also several, perhaps more amenable explanation techniques. These logic-based explanations, maybe they are more fitting into this kind of context. But no, other things are also fine. Yeah.
Thank you.
Okay. All good. Okay, then I can go to the rest of the talk. So basically here is state-on verification. And as I said a bit earlier, for these two parts, basically we use formal methods, but we don't do verification. We do something else. So for the explainability part, basically what we're going to do is basically use the abstractions. So we're going to abstract the models, but then without using, so we will not use the abstraction to do the verification, to verify, I don't know, classification, robustness, saliency map, robustness, whatever it is. But we're going to use this abstraction to explain what the model is doing. I'm using explainability, interpretability a bit interchangeably. I have to apologize for that. But yeah, in essence, explaining what models are doing, this is what I mean. And there's a bit of tension in machine learning between how the model performs and how easy it is to explain or interpret. So we have very easy models to explain, very easy models to understand, linear regression, decision trees, and so on. And then but they don't perform very well in practice unless the problem is small and constrained. And then we have this, well, I mean, I have to add other ones, but let's say all neural networks and, all the new other things, they're very accurate, they perform very well, but it's very hard to understand what they're doing. So for this part, I want to go, so the previous part was on neural network. To change, I want to talk about support vector machines here, just to see some other different model. So if you don't know what these are, they're basically planes, separating planes. So basically, we have this separation, well, we can call them curves, because when you have nonlinear SVMs, these are basically curves, but in essence, you're separating points in the space that are classified into different classifications. And these curves are supposed to, or these lines, are supposed to minimize the difference, or the distance, the margin is called, between the closest point in the space that are classified differently. And these are called the support vectors. So to give you an example, we have basically, let's say this line, we have 2 dimensions. These are the 2 support vectors. So this line here is our SVM. So this will basically separate all the points in this part of the space, will be classified as a circle, so -1. All the points in this part of the space will be classified as a triangle, so 1. What this is basically, we take the value of the classification times these are the weights that we learn during the training. And these are the support vectors, and this is the input vector, okay? So this is the SVM. You give it an input vector, it does these computations, and will tell you whether it's a circle or a triangle. And this is a linear SVM, so it's a very simple case that we can rewrite as a function as well, so as this line here, which is basically this function to which we apply the sine function to basically go on this side or on this side. So this is the example I will use for the rest of this part. Of course, we can do more complicated things, especially when the points in the input space cannot be linearly separated. In this case, typically what we do is we map them into a feature space, which is a higher dimensional space, but where we can find a way to separate them linearly. And the map from this to this is done through what is called the kernel function, and there are various kinds of kernel functions. There's these polynomial functions, radial basis functions, all kinds of things. We don't need to know the details about that, it's just know there's a mapping between the input space and this feature space that somehow works. So what I want to propose for this part, it's basically you have your input space, and you map, through this function, you map it to a higher dimensional space where you can find is a plane that separates the points. This is, the idea is, with these SVMs, you want to find these linear planes, but if you cannot find them, then you just go to a higher dimensions where you can finally find a linearly separating plane. Okay, so what I want to do is basically find explanations for SVMs. And so in machine learning, there's a category of explanations techniques that are called feature importance measures. So basically, these measure the contribution of the input features to the predictions. And there are tons of kinds of this. The most popular ones are these ones. And they have different flavors. So they can be local explanations, the global explanations. So local explanation, they explain one prediction. So you give it an input, and they explain why that input was classified in a particular way. Global means they explain the behavior of the model over the entire input space. Model specific really depends on the model on which that they are used to interpret. So they can be specific to SVMs or can be used for any other model. So these are the most common model agnostic explanations. And then there is another distinction, which is this performance or effect based. So the performance based, they basically decide the importance, they measure the importance of the features by checking, in essence, whether changes affect the performance of the model. So they need to know what are the correct, it depends on the data set, right? So, and they want to see how the accuracy of this model degrades with respect to the given data set, for instance, when we apply some changes. And the effect, so they need to know basically the true labels of the points on which they are tested. The effect base, they simply look at how the prediction changes, but they don't need to know whether the prediction is correct or incorrect. So what I'm proposing is another feature importance measure, but that we call abstract feature importance. It's specific to SVMs. We can use it for local or global predictions, explanations, and it's effect-based. So it doesn't depend on a data set. It really just looks at how the output changes with changes of the input. What else I wanted to say about this? Yes, the other thing that we wanted to do, to have something that was very fast to compute. Some of these techniques, some of this, like Lime or SHAP especially, they're very costly to compute, or PFI even. They're very expensive to compute, and we wanted something very, very fast. The question is then, why do we need another feature importance measures? There are various reasons, so I collected some. We don't need to read them. For like this most commonly used ones. The essence of it is that all these explanations, they make sense, but they are not grounded in any formal guarantees, right? So what we wanted really was something that it comes from an approximation that is correct by construction, done by abstract interpretation. We didn't want to depend from a data set or the accuracy of the model. We wanted to be extremely fast, as I said before, and we wanted to support both linear and nonlinear kernel functions, so linear and nonlinear SVMs. Because before this work, the explanation techniques that were available in the literatures for SVMs, they were all supporting linear SVMs only and not nonlinear ones. So the way we decided to do it is to use abstract interpretation, as I hinted already. Essentially, we have an abstraction of the input of the SVM, an abstraction of the computations of the SVM, and abstraction of the output. Then typically, what we do with this output abstraction is we use it for verification. And what we wanted to do here was to use it for explanations. So the kind of abstract domain that we used in this case was this reduced affine form abstraction. It's a sort of a zonotope abstraction with less terms. I'll show you what it means. So this is the SVM, or at least, well, let's say, okay, an SVM, what it does, it takes a vector of real numbers as input. It does the computation that gives a real number as output. It applies the sign function, and then it classifies into a circle or a triangle, let's say. This is for binary classification. We can do more, but yeah, the binary classification is a simple case. With the abstraction, we're gonna use basically each input vector, each value in the input vector will be abstracted with this reduced affine form. I will show you what it is. So we're gonna have a vector of the reduced affine forms. We're gonna do the abstract computations with the SVM. We're gonna get a reduced affine form as an abstraction of the output. And then we could do this verification thing, but we're not gonna do that. We're gonna stop here, basically. Okay, so what are these reduced affine forms? They're basically linear expressions. So there is, in the linear expression, there's gonna be this epsilon I terms. So each of these epsilon I terms will, in essence, represent the input dimensions. So here there are 2 dimensions, for instance. So we're gonna have an epsilon term for x1, an epsilon term for x2. And then, so this is a linear expression, right? So we're gonna have then an extra term, this epsilon r, that will accumulate essentially all the errors that we can do with the nonlinear operations. Okay, and then it's an abstraction, so we also have top for anything that we don't know how to represent. I'll give you an example. This is the example from before, this line from there. So we have this SVM, this line here is this SVM. Then we typically apply the sign and do the classification, but we don't care, as I said. So let's say we want to know, basically abstract this SVM in this region of the input space, okay? So this is our set of input vectors. So the reduced affine form will give us this. So basically we have minus 0.5 epsilon 1. This will be basically abstracting this direction, so this side of the dimension, this box here. And then we have this other expression, 0.75 minus 0.25 epsilon 2 for this other part of the space. Okay, so together they represent this input space here. And then we do the computations of the SVM with this abstraction. So what it means is basically instead of the input vector, any input vector, we're going to have this, which represents several input vectors as input. And then we do the SVM computations as if it was just a vector of numbers, right? So we're going to have the weights are the same, the V1, this one, the support vectors are the same, so we just do the vector multiplication with the expressions here. And then we do the linear computations. And this gives us basically another expression down here that represents the output of the SVM, or abstracts the output of the SVM for all the inputs in this space. Then typically, I keep repeating this, but then typically you use this to then check if maybe the classification is robust, so you want to know if all these points are classified as circles, you can do that. But we really don't care about this. We want to stop here. So the question is, how can we use this abstraction to then decide which feature is more important in the input space or not? What we observed was that basically, well, since all these epsilon expressions here, they somehow relate to the input dimensions, then the coefficients can also give us an indication of the importance of those dimensions in computing the output, okay? The catch is that, well, depending on the precision of the abstraction, we may have a big extra term here that will catch a lot of information, so will somehow dilute the information that we have on the input dimensions. So if the abstraction is precise enough, then the coefficients here gives us a pretty accurate picture of the importance of the input dimensions. If it's not that accurate, if we have a lot of nonlinear operations, this term will grow and then will give us less accurate explanations. So we wanted to try this out, basically. So before I show you the experiments, the results, I can give you an example to make it a bit more concrete. So let's say we want to explain our SVM on the entire input space. The entire input space is represented as these two epsilon 1 and epsilon 2 terms. Yeah, I don't have the time in the talk to tell you how this reduced affine form abstraction works, but basically there are rules on how you convert an interval into an expression of that form. So it's a very standard thing to do. We do the operations of the SVM in the abstract version, and what we get is this expression here. So we have 0.5 epsilon 1 minus 1 epsilon 2, and what this tells us, if you look at the coefficients in absolute value, is that this epsilon 2, so x2, is twice as important than epsilon 1, so then x1 then. And if you look even further, if you look at the SVM written in primal form, so as a linear expression, you see that these coefficients actually match exactly the coefficients that we get in that linear expression. And this is because it's an easy case. It's a linear SVM. Of course, when you have nonlinear SVMs, there is no match. We don't have a primal form, but there is no direct relationship. But in the experiments, we saw that this was an pretty accurate measure of the importance of the features, except when the abstraction was not precise enough. So to give you an idea, yeah, I still have a bit of time, okay. To give you an idea, we had considered different SVMs trained on this German data set. Just as an example, we took as a baseline, basically what we did was sampling randomly in the input space, perturbing the feature, and seeing how the result changed. So we had a very basic baseline, and then we compared our importance measure with the permutation feature importance, because well, we could just call a library to use it, and it was very easy to do. So what we did was basically compute these grades for the features. So basically we associated a grade of importance to all the features. Sometimes when we couldn't necessarily distinguish, so we can distinguish if we want to be very fine, we can distinguish between different features, but we decided to group them based on if they had a very similar importance, we decided to group them. So basically these are the first 3 features are the least important ones. These 2 are a bit more important and so on. And then what we did was comparing with the Euclidean distance between basically our grades and the grades of the baseline and the grades of permutation feature importance. So permutation feature importance, what it does is it takes, for each features, it does a perturbation of the data set, of the row, of the values in the specific feature row, feature column of the data set, and sees how the accuracy of the model degrades given that data set with shuffled rows in that column. And based on that, it decides whether the more it degrades, the more important the feature is, and vice versa. So then we computed the distances from our measure, our grades, and the grades of PFI to the baseline, and also checked how long it took to do the things. And in all cases, you see that we are always closer to the baseline. But the grades, so for instance, here for the polynomial SVMs, you see that the abstraction is not great. So we don't quite match the grades of the baseline. We do identify the most important feature and one of the slightly less important ones. But beyond that, we do a bit whatever. But PFI does worse. So for PFI, this is the most important feature, which is the least important one for the baseline. So even if the abstraction is not that precise, we are still closer to the baseline than this PFI. And we do much better for the other SVMs. So the linear case, obviously, because it's really essentially one-to-one match with the linear SVMs, and still good with the radial basis form SVMs. And this was for one data set. Of course, we tried with different parameters for the baseline, number of sample nodes, how far we go with the perturbation of the nodes, and different data sets. And in all cases, we are still better, closer to the baseline, even for the less precise abstractions. So interesting opportunities to work there on abstract domains, if you want, really are on these polynomial SVMs. The abstractions there are not good enough, so there is more work that can be done to make it better. And then we also compare to Lime as an interesting, so this was for the local explanations. So what we did, since Lime uses a different way to compute the local neighborhood of a point, we compared with basically the way Lime works and our local explanations to a different size of neighborhood, so different size of epsilon ball around the point. So this is very small, slightly larger, and up to the global, so basically using AFI on the entire input space. And we compare the distance between our grades, our importance measures, and what Lime was computing. And in most cases, in fact, we were closer to Lime when we were explaining the entire input space rather than the local explanations. So we found this curious. We don't know exactly why that is the case. But yeah, there is certainly a mismatch. So either we are wrong or they are wrong, or who knows. In this direction, we also have a bit of an ongoing research on this sort of abstract explanations. So other kind of explanations that are somewhat logic-based. So essentially, finding the minimal set of features that can ensure the classification outcome or change it if they are modified for various kinds of classifiers. And here, what is interesting for this is that maybe we can use abstractions to do this to find this kind of explanations. This similar kind of abstractions as the one that I show you can also gives us different kind of explanations of this kind. Okay, for the last bit on training, this is shorter, so don't worry. So yeah, I talked a lot about the deployment phase, so I wanted to touch a bit on the model training phase. So here, a lot of the work is done on the machine learning community, of course, and a lot of the work is still tries to address this adversarial examples problem. So the idea is they try to use training to make the neural networks, so the models, more robust. So in particular, well, they want to find parameters of the models, the weights of the neural network, for instance, that minimize what is called the worst case loss, so the maximum error that the network can make in a neighborhood of a point. So basically you have the points that they use for training, and you want to minimize the errors, so when the network is wrong. So you want to find the parameters that make these mistakes smaller in that neighborhood for each point, basically. So what that means is basically you try to make the network more robust by construction, so finding the parameters that try to make the classification more robust. But the problem is that this worst case loss here is very expensive to compute. In practice, nobody does that. But in the machine learning community, what they do is they use a lower bound to this, which is basically using quick ways to finding adversarial examples to points and adding them to the training set, augmenting the training set with those. Of course, we don't get any guarantees, right? So the machine learning, the formal methods community decided to then instead use an upper bound on that. So say, okay, we use, so we modify the loss that we use for training to use an upper bound. So for each point in the training set, we're gonna train it using an upper bound on this worst case loss. What is the problem with that? In practice, this certified training thing here, well, in theory it gives guarantees. In practice, it's pretty bad. Because in practice, what you get, this is a comparison between the state-of-the-art in machine learning, state-of-the-art in formal methods. So this is the best current techniques for doing certified training. This is the best techniques for adversarial training. And this is the measure of how well these models resist to adversarial attacks. For certified training, you get some certified accuracy, but the empirical accuracy, how well they resist to adversarial attacks, is very bad. The best techniques in machine learning, they get to some 70% against very strong attacks. Here, what they get, even against very weak attacks, is 35%. So it's a big gap, more than 35% gap. So it's not interesting for the machine learning community. Also because when you look at the standard accuracy of these models, here you get 52%, where here you still get a pretty good accuracy of 93%. So in practice, any model that you train with certified training is useless for the machine learning community. So what some people have been doing is doing some sort of hybrid training. So essentially using a combination of adversarial training and certified training, maybe linear combinations or other kind of combinations. So basically during training you can tune how important is the certified training component and how important is the adversarial training component. And you can adjust this during training, you can adjust your training schedule, you can do all tons of things. But this in practice can work pretty well. So we haven't, at the time we had not formalized this way, but we understood later what we were doing. So I want to give you a bit of a, so we did some hybrid training and we did it on this random forest. We realized later what we were doing, but So random forests are basically sets of decision trees. So you have a bunch of decision trees and then you have a voting mechanism to decide the final classification. Voting mechanism can be majority or average or whatever it is. Okay, I will not say more than that. They're very simple models in themselves. They become a bit more complicated when you make them into a forest. So what we did back then was we considered fairness, so individual fairness, which is as a variant of local robustness. So what we wanted was to make some sort of certified training technique that improved the fairness of these models. But we did it in this hybrid fashion. So we basically used some training technique where we are also using adversarial training in some ways. And what gave us was basically models that were not degrading the accuracy that much, but were gaining a lot in this certified robustness, if you want, so certified fairness. The other thing that we did, that machine learning people liked a lot, was basically during training with a regular random forest, you basically have to tune a lot of the parameters. Here, the training process that we had designed was done in such a way that all these parameters were somehow inferred automatically during the training. So what we did was, yes, one other interesting bit was the size of the trees that we would get. They were actually much smaller than the ones that we would get with regular training. So what we thought was, why don't we get the parameters that we inferred with this training process and use them to tune the regular training of decision trees or random forests. So we did that, and as a result, we got something in between. So we got something with the regular training, but just with these hints from this certified training or hybrid training process. We got something with a very small decline in accuracy, but a big improvement, like 20%, almost 20% jump in robustness. And the size of these models was also much more contained, so easier to understand what they were doing. And this was actually very much appreciated back then. So it was an interesting way of using formal methods to do something useful for the machine learning community. And then we have a new results in the space. Last bit, I promise, I'm almost done. Basically, we did use the hybrid training, now that we understand what hybrid training is. And we used it to do adversarial training. So one of the problems in adversarial training is that it can be very costly as well, especially when you start doing PGD-10 or this kind of things. So there is a branch of the machine learning community or the adversarial training community that uses this one-step attacks to mitigate this cost with good trade-offs. And what we did was basically show that in certain conditions, we can use hybrid training to get better empirical robustness than plain adversarial training at a smaller training cost. So we can do better than PGD5 in some cases at a smaller training cost. We're not yet as good as PGD10, but so it was a good example of how formal methods can be useful to machine learning in some ways. Okay, so with that, I think I concluded my overview of things we can do. Of course, I hope I maybe gave you some ideas of things where you can, directions that you can look into. And I'm happy to take more questions. Thank you.
So thank you, Caterina, for the very interesting talk, as usual. Are there questions?
So thanks for the very interesting talk. What do you think will be the best way to communicate with the machine learning community? So will publishing formal methods paper in machine learning conference be enough, or should we need more general or deep kind of communication to integrate them? What's your experience about that?
So publishing is hard. Just publishing is very hard. So what I found useful is actually hiring a postdoc that comes from the machine learning community that is more open-minded than others. But it was a very fruitful collaboration. I learned a lot about, you know, their world, and in the discussions we understand that we speak different languages. You know, little by little, I don't know. Eventually, I think maybe workshops would be nice, but I think we need to gather a mass of people that want to talk to each other first. Yeah, it's not easy yet.
Thank you.
Yeah.
Other questions?
I just want to follow up previous question. Like, do you know why that so hard for the machine learning community? Is that the reason they don't care about the correctness at all, or it's just?
Yeah, so there is a part of that. So in a lot of their problems, adversarial training is good enough, right? That they have all this heuristics to measure the quality of their models, and for them is good enough. They don't work. They don't come from the same community, right? So they don't have the safety critical issues to worry about. We come from a different, we have a different mindset, so we're all worried about using these things in safety critical situations. They are much less concerned about that. And also, yeah, it's also a problem of the language that we speak. So we care about this even complex properties. So in my tutorial the other day, I was talking about hyper properties of neural networks and so on. They don't care at all. Like for them, this adversarial example is the biggest problem that they have, and this is where the whole community is doing research on. Other properties, they really don't even care or consider that
until the huge problems came out after.
Yeah. But for now, it's a bit like that.
I really liked your like introduction of AFI. Have you like published or put a preprint or anything like explaining it?
Yeah.
Like
So this one is in VMKI 2024.
Okay.
I don't know if it's extremely well written.
Okay.
But
well,
yeah, this is where it was published, the work. Yeah.
Okay, I'll look into it. Thank you.
Okay, thanks.
Any other question?
Well, if not, thank you. You've been a very nice audience.
Thank you. Thank you, Caterina, again. So now we have the first full paper presentation of NSAD. The title is Towards an High-Level Linter for Data Science, and the speaker is Greta Dolcetti.
So, thanks, Michele, for the introduction. So yeah, I'm Greta Dolcetti, and today I'm going to show you our latest work towards a high-level linter for data science. This is a joint work with Agostino Cortesi, Caterina Urban, and NSAD Zaffanella. Throughout this presentation, we will start with some context and motivation that inspired us for this project. Then we will see a little bit of background for data science, and then we will see what we define as code smells in data science and a short list of examples. Then we will delve in the more static analysis related part, talking about our abstract domain design and the type rules that we used throughout our analysis. We will briefly talk about the implementation, and then we will conclude with some future work that we have in mind. So, as you may know, in recent years, the volume of the data that's available on the web for the user has exploded. And this has led to a consequently explosive growth in the field of data science. But on the other hand, we also know that data science is an inherently interdisciplinary field in which expertise is coming from different areas, such as computer science, biology, bioinformatics, and statistics, come together and converge to focus and work on one thing, the data. So this complex nature of data science makes it subject to subtle yet result-compromising mistake. And in this context, it is our goal to develop a high-level linter for data science code smell. But I want to do a disclaimer. So it's absolutely not our goal to develop some kind of prototype that is an oracle and dictates to the user what they have to do with absolute certainty. Instead, we want to provide the user with a tool that provides them with possible unwanted behaviors and encourages critical thinking about the adopted solution. So, as I said, data science is quite complex, but different phases can be usually recognized in the data science pipeline. For example, data scientists usually start with the exploratory data analysis phase, also called EDA. In this phase, they try to study the data that they are working on, and they do so by computing some kind of statistical indicators, such as mode, mean, or median, and try to understand what's the statistical distribution of the data that they are working on. Then, after they finish the EDA, it is a common practice to proceed with the data visualization phase, in which graphical plots of the data are created to have a better visualization of the data and to better see if there are like any outliers or to better understand the statistical distribution of the data. Once we have done that, it's common to proceed with a more technical phase, which is the data cleaning and pre-processing phase. And during this step, the data science remove the outliers, so values that are too big or too small, for example, and they apply some transformation to the data, so to make them more fitting to the goal that they want to solve. This kind of transformation includes some kind of standardization or normalization. Thence, when the data are ready to use, it is common practice to build a machine learning model on them, to train the model on the data, and to conclude with the performance evaluation of that model. And I want to point out that errors can happen in each one of these phases. So, as I said, there are some challenges in analyzing data science due to the complex nature. So data science often requires the use of many different libraries, and it is often performed in permissive dynamic languages, such as R or Python. And on the other side, the data scientists often adopt an interactive execution over a sequential execution that we are more used to. So to tackle this kind of issue, in our proposal, we target the most common libraries. So we target NumPy, Matplotlib, scikit-learn, and of course pandas. And we propose an abstract type system to deal with the dynamicity of the language we chose, which was Python. And we decided to ignore interactivity. So if we are to analyze a notebook, we simply consider the code of the notebook from cell 0 to cell L sequentially. So as I said, due to the explosion of data science field, many tools have been developed. For example, we have some low-level linters tools like PyLint that provides the user with some hints about possible guideline violation. We have some type checker like MyPy, but this kind of type checker often relies on Python concrete annotation that luckily are often missing in the real code. We had some data validation tool like Pandera that work on the concrete code, and they perform some data schema validation or some statistical testing on the concrete data. As I said, each one of the tools has its own kind of limitation in detecting high-level data science code errors. So again, it is our goal to infer a reason about more abstract data types and to potentially capture a broader and less conventional set of errors and code smells. Now we can finally define what we intend as a code smell in data science. So in this context, we consider a code smell an action that is legal in the language of choice, so that it does not raise an exception in Python in this case, but it may be a logical or methodological mistake, and it may potentially lead to incorrect results. But I want to start and point out what we are not interested in. And I want to do that using a very, very small example. So in this example, we have a data frame containing one column whose name is fruit, and this is a string type column. Then our data scientist wants to compute the mean on this column. But since this is an attempt to compute the mean on a string type data frame column, this results in a value error exception. So in this case, the program terminates, an exception is raised, and the error is already handled by the language interpreter. So this is the kind of thing we are not looking for. We are not interested in that, because if the user wants to continue development his data science code, he has to deal with that because an execution is already raised. So here, the idea is that we want to focus on more subtle mistakes that do not interrupt the execution, the program execution, and therefore can be more subtle to spot, and they can silently propagate their error throughout the code. And now we can see some kind of what we intend as code smells in data science. As I said, errors can happen each one of the phases that I've showed you before. For example, we can have some kind of misleading data visualization. Here, in this example, we have a data frame containing two columns. One was named fruit, and the other one is amount. One is a string type column, and the other type is an integer type column. Then, since we are in the data visualization phase, and we want to plot the data that we are working on, our data scientist calls the plot function. And the problem is that the plot function, the default plot function, creates a line plot, which you can see here on the left. In this case, no exception is raised because this is legal in Python, this is legal in pandas, but this plot can be deemed inadequate. Why? Because the line plot implies continuity where none exists. What's the continuity between apple and banana? And those are strings, so it's difficult to consider them as numbers. Of course, in this case, we have a better alternative, which is for the user to use the bar chart function always provided by matplotlib. In this case, we create the bar chart that we can see on the right, and this is better for categorical data. It suits better the plot for categorical data since it creates a bar for each category, and the height of the bar is the value for that category. It does not imply continuity, so it's a better option in this case. That was an error, kind of like easy to spot because we can see that error, but we have more silent errors, such as misleading central tendency measure. This is a very toy example in which we have a data frame containing T1 and T2. And in our example, those are the times that, as we often do, our data scientists measured during some experimental execution. And then the user wants to compute creates a speed up column, which is the division between the old time and the new time. Then the user wants to see, on average, how fast they are. So what they do is that they compute the mean on the speed up column. And this is legal because the speed up column is a column of numeric values. But we have a problem. The mean, the default mean, computes the arithmetic means. And the arithmetic means of ratios can be skewed by extreme values. In this case, as I said, this is legal, so no exception is raised. But this mistake can lead to very different results. Because when we have like ratios, a better alternative exists, and it is to use the geometric mean, since it's more appropriate because it better captures the positive nature of the data that we are working on. So what I want to point out in this case is that even if this is a very, very small example, the results diverge quite a bit because one starts with 1 and the other one starts with 2. And this error can be very, very difficult to spot if we do not know the existence of the mean function, for example. Then, as I said, we can have error also in the data preprocessing step. And this regards the central tendency measure of scale data. In this case, we have a data frame containing just one column, x, which is a column of integers, and then the user creates a standard scalar offered by the scikit-learn preprocessing library. And then the user applies the fit transform function offered by the standard scalar on the column that he has, and creates a new series, which is the standardized column. And then the user computes the mean on this kind of column, which is legal because this transform column is still a column made of numbers. But, so no exception is raised, this is legal, but this zero result that we can see here is completely non-informative because the problem is that in standardized series, the mean will always be 0 by definition because standardization means that we are transforming the data so that they are distributed as a normal Gaussian with mean 0 and variance 1. In this case, of course, we have a better alternative, which is to compute the mean on the unstandardized value, so we capture the real mean of the data that we are working on. So to deal with this kind of code smells, we created an abstract domain whose purpose is to model data science concepts. And we did so by creating a hierarchy of abstract data types that sometimes are more abstract than the concrete types and sometimes are more refined. Here you can see two small parts of the domain regarding series and array. Series and array are the same as the concrete types that we have in Python language, but we have more refined types. For example, we have standardized series, normalized series, ratio series, Boolean array, and string array. For this one, we are like taking into consideration how these series are created and so their nature and how the values that can be in them. And we use them to capture some code smells. But as I said, we can also have more abstract data types than the concrete ones. And this is the case for the numeric data type. So in this context, in our prototype, we are not interested in distinguishing between integers or floating point values. So in the concrete, if a value is an integer or a floating point, it will have an abstract data type that is numeric. So to perform our analysis, we use some kind of type rules. And our static analysis computes and propagates this kind of type information by maintaining an abstract type environment gamma. At the beginning of the program that we are to analyze, the newly encountered variables are added to the type environment gamma, and they are mapped to the top element because we don't know anything about them. But if we are lucky enough to have some concrete Python type annotation, some Python type ints, those annotations are also taken into consideration, and we start the analysis with some types and some more information. Then, during our analysis, we have to deal with library calls. And our analysis completely ignore the concrete semantics and the actual implementation of these library calls. And it only relies on abstract type data type signatures that we have encoded as type rules. During the analysis, if no type rule exists, or when we are trying to merge two incomparable types, then our result will be set to top. As a peculiarity, we also have to deal with some, of course, peculiarity of the pandas library, such as the in-place calls, for which we will see an example in a few slides. Now we can see some example of the type rules that we have encoded in our analyzer. So for example, this is a type rule for a library call, read CSV. So this is one of the most common calls from pandas, because in the concrete, it reads a file name, a CSV file name, and it returns a data frame object. But when we do that in the abstract, we have that the result is an abstract data type of type data frame. Here you may note that we have not any premises of any type on the file name argument, and this is absolutely on purpose because we do not want to pose any requirement on that, because in the concrete, so if the data frame, if the file name is missing, if it's not in the correct format or anything like that, an exception will be raised. And again, the data scientist will be forced to look into that, so we only consider the supposedly correct execution of that. If anything happens in the concrete, we are not interested in that. Similarly, we also have to model operations. So in this case, we are modeling the division, and we say that given two elements whose type is series or a more refined type, the resulting type will be a ratio series. And this rule is meant to capture the possible speed up values and the related warning that we have seen before. Of course, we can also model more complex call in which we can specify different types for the caller and the argument of the call. This is the case for the fit transform call, in which we have an element of type standard scalar that calls the fit transform function of an element of type series. And this results in a standardized series that we have seen before. We can have also some case on homologous, or the same name for the function, and of course, we can specify that on the element that is calling the function. So we have a similar rule for the min-max scalar that returns a normalized series, not a standardized one. So we can have different levels of refinement and specification. As I said, we also have to deal with the in-place call. Now, we know that in the concrete, the in-place flag can switch between functional and imperative side. And here we have a result. This call in the concrete, if it was not in place, will return a series element. But since this call is in place, this in the concrete will return the non-Python object. And so this assignment in particular of this example is likely a codesman, because then the user can perform and call some kind of function on the non-object, which will result in a codesman. So to handle this particular peculiarity of pandas, we encode that in a type rules that says that if, in this case, a series or a more refined type calls some kind of function with the in-place flag equal to true, we return a special abstract data type, which is non-red. And if non-red is assigned, this triggers a warning. speaking on warning, this is an example of the warning that we issue. So gmin warning is definite, and it says that the min function at line 7, the column speed up is a ratio series, and then gmin should be used. So what are the kind of information that we provide the user with? So we provide the user with the warning type, which is usually quite informative and intellectible. We provide the user with the severity of the warning, which can be possible or definite, with the function that caused the warning to be raised, the line in the code in which the warning happened, and some type of abstract type information about why the warning was raised that we retrieve from our abstract state. And then we provide the user with a possible solution if that exists. Speaking about the implementation, we implemented this prototype by extending the Lyra static analyzer. So Lyra is a static analyzer for Python, written in Python, that will takes in input the Python AST, creates a CFG, and then analyze that using domains and the abstract interpretation framework. In our case, we focus on Python that was extracted from the Jupyter notebooks, and as I said, we only consider the sequential execution of the Jupyter notebook code that is inside them. And on that Python code, we perform a forward static analysis, and we do that with a no-relational abstract state that maps each variable to its abstract data types. Now, we can finally see an execution example. So we are analyzing this snippet of code. We are importing some libraries. We are assigning a list to a variable x. We are creating a data frame and assigning it to a variable df, created a standard scalar, assigning it to the variable sc. Then we apply the fit transform method to the series of our data frame and save that in a new series, in a new column. And then we are to compute the mean on that column. So when we analyze the program, since in this case we are not lucky enough and we do not have any kind of Python concrete type annotation, we start with all the variables that are mapped to top because we do not have any information about that. Then we analyze the first assignment. And after the first assignment, we can say that x is a numeric list. And this is because the right-hand side of the assignment is a list display containing just integer types. Then we analyze, Then we analyze the second assignment in which we create a data frame object, and then the df is assigned to the data frame abstract data type. We do the same in a very similar way from the standard scalar constructor, and then C is a standard scalar. And we use this kind of information when we are analyzing this more complex code. Because here we have that there is a standard scalar calling a fit transform function on a series of the data frame. And therefore, the left-hand side will be assigned to the abstract data type standardized series. And then finally, we come to our problematic code. So here we are computing the mean on the standardized series. But I want to make you note two things. The first one is that in the end, x mean will be of numeric data type because this is a legal action. So if the user is really sure that they want to do this, they can do it because in the concrete execution, this will be a number. But in our abstract analysis, we are issuing a warning, and we say that we issue a scaled mean warning, which is definite, and it was caused by the call of mean on the f of x norm at line 7, because the f of x norm is a standardized series, and therefore the mean may be not meaningful. So once we have done that, we conclude our analysis, and we have the result about our abstract data type. So speaking on future work, of course, we are planning to extend the design with new data types and new rules. We want to capture new warnings, and to do so, we will probably need feedback from data scientists, but also if you have any kind of suggestion, please reach out to us. Then we want to improve the precision of our analysis by using some kind of data schema, either provided by some user annotation or by computing the concrete info call on the data frame that we are analyzing. We are also planning to run an experimental evaluation on real Kaggle notebooks, and once our prototype will be robust enough, we plan to integrate that into existing workflows in the form of like a Visual Studio extension. So to conclude, we argued for the development of a linter for data science, which is still in progress. We focus on high-level data science code smells. We use a high-level abstract type system, using abstract type annotation for library codes during the analysis, and performing checks for library codes for consistency with those annotation, either way issuing a warning. And with that, I conclude my presentation, and I'm happy to answer any question if you have any.
Okay, thank you, Greta, for the nice presentation. Are there any questions?
So very nice talk, very interesting. You didn't say so much about related work. It made me think of some old work that was done on dimensions and dimension inference in programming languages. Would that be something related to what you're doing?
Oh yeah,
So you
there
could
are
say
some like more in depth. You can find more related work on the paper. There are some other like related work that also use abstract interpretation, but the fact that they usually work at a lower level, and instead we reason on some high-level code smells, which are not so common captured by this kind of linter. That's, yeah, if that answers your question. I'm not aware of that specific kind of work.
So it's just you can say that this integer measures a distance and this integer measures.
Sorry, can you repeat that again?
So you refine your types and you say this integer actually represents a measure of distance, and this one represents time.
Okay.
And so you can catch certain errors.
Oh, okay. I was not aware of that, but we can maybe integrate that, because the more information you have about the type that you're using, the more code smell you are able to capture probably. So yeah, thank you.
Thanks for the talk. I actually have two questions, and the first one is you gave few examples in your introduction about the no exception races, right?
Mm-hmm.
I wonder why it seems so obvious to me, but I can understand somehow Python is a dynamic typing. They probably won't check until at the runtime. Is that exceptions is not raising because the programmer didn't actually capture it, or it's because no exception from the library that the code?
I think that the libraries is so permissive that it allows you to perform these kind of errors, because, like, for example, the plot one, I mean, for someone, if you know that your category have some kind of continuity, something like that, it may be okay to do that. But I think it's due to the permissivity of both the language and the libraries.
In that case, do you think, I know that the Python, they also introduced the optional static typing, right?
Yeah.
Would that a type hint can help stop this kind of problem?
Yes, probably yes, also because you can do checks, but the problem is that in real code, like we explored many by manually Kaggle notebooks that you can find online, type hints are not really that used in
right.
data science. Also because, as I said, data science is often performed by people that are not born as computer scientists. So they care about the analysis, they don't care about that much about static typing.
Yes.
So, I mean, that would help for sure, but if you look at the documentation of type-ins, the Python organization said that they are not willing to make that some kind of standard. It's just there. If you want to use that, you can use that,
yeah.
but they are not forcing you to.
Okay, a second question, sorry. How many typing rules in your paper do you actually, in the end, have?
Okay, so we modeled the semantics for around, I would say, 200 something library calls among Python, pandas, scikit-learn, NumPy, and matplotlib. Some of them are really simple. Some of them have like many, many cases and different abstract return types, so they are quite complicated.
In that case, do you think, I'm not sure how the Python interpreter that actually does the type checking at all, or do you think you can incorporate these typing rules into that part instead as a standalone?
Ideally, probably yes, but at the moment it would be probably faster and easier to perform an analysis on the code that you have. So
Cool.
yeah.
Thank you.
No, you're welcome.
So, okay. Just last question.
Thank you. Thank you for the talk. Do you plan to support, sorry, you talked about there were rules for these library functions, right, that are known. Do you plan to support users being able to define their own class objects and calls and then their own rules that they want?
Yeah, that's another part of future work. We are planning to also create some sort of DSL in which you can express your rule, your abstract data types, and therefore you can make the analysis more tailored to your needs. So yeah. You're welcome.
Okay, just last quick question.
Yeah, so very quick but a related question. So yeah, when you present things like this, it seems like it would be very nice for users to be able to define their own code smells, specific to their kind of applications. So do you have any?
Yeah, it's related to that. Yeah,
okay.
If you can, the idea is that once the prototype will be mature enough, you can use a DSL. You can specify your abstract types, for example, your domain and the thing that your library calls returns, and therefore you can also specify your warnings, because maybe also with using our warnings, you may say what you are interested in and not interested in. That would be an idea, but also, of course, it would be nice to specify so your warnings, and we will work into that probably.
Okay, let's thank Greta again. So this concludes the session.
Oh, cool. Okay. Hello, my name is Anthony, and I have the pleasure of presenting some work I did on floating point error analysis using step functions. So first, just a little bit, floating point numbers are ubiquitous in computer science. We've all used them before. Anytime you want to work with real numbers, you end up using floating point numbers. From high consequence systems such as avionics to industrial control systems to machine learning. They're undergraded at everything. Despite this widespread use, they're pretty imperfect. And this imperfection causes a deviation from if you were doing an exact calculation. So I've got kind of a silly example here, where if you write in JavaScript 0.1 plus 0.2, it doesn't equal, as you would expect, 0.3. And part of this is because 0.1 is not exactly representable in the double precision format. While this is kind of a trivial example, you can see how this sort of subtle error in a more complex, oh yeah, hello. Okay. You can see how in a more complex system, this sort of deviation from what you would expect can propagate and cause different errors in behavior. So the goal of this work is to help programmers manage this error and understand really what's going on. And so the way we went about this is we developed an abstract domain using step functions that will not only give them a bound on the error, but also give them some insight into the nature of the floating point error in their program. Before I dive into the abstract domain, though, I need to talk a little bit about some of the fundamentals of floating point numbers that we leverage in our abstract domain. So some background here is a floating point number is represented by a mantissa, M, a base, beta, and an exponent, E. The format is actually defined by the base, which remains constant for all the floating point numbers in the format, and a maximum value on the exponent. And so the only things stored in memory are the mantissa and the exponent bit patterns, and to get the actual value out, you have to run this equation. This format has some interesting consequences for the behavior of floating point numbers. Here we've got a diagram of the real number line, and each of these vertical bars represents a representable floating point number. Here's an example calculation where we have two representable floating point numbers, A and B, and we multiply them together, and we end up with a non-representable result. When this occurs, you have to round the floating point number. You have to round to a representable floating point number. And this difference between what you would have gotten exactly and what you're forced to store in the computer is the source of this error, and this is called the round-off error. However, this is a little bit of a simplified diagram, because in reality, you get something closer to this, where the difference between representable floating point numbers changes in size depending on where you are in the number line. So you can see around 0, we've got a certain step size, and then as we pass this boundary, we end up with a larger step size between adjacent floating point numbers. These regions are called binades, and they'll become important in our analysis. The cause of this is the exponent. So when you're incrementing a number, a floating point number, you're incrementing the mantissa or decrementing, and the actual change in value is going to depend on what the exponent is. As the exponent increases, your change in your step size is going to increase, and if the exponent goes lower, then your step size is going to go lower. And one of the key things here is as you get closer to 0, you're going to have more and more fidelity towards what real numbers you can represent. This also has another knock-on effect, which is there's a lot more binades near 0, which will become a little bit more important later on. I've been saying the word step size, but what I've been referring to as step size is typically called ULP, or the unit in last place, which is just the distance between the two nearest representable numbers. Because this step size changes depending on the magnitude of your variable, you can think of this as a function from some real number to this distance between the two nearest numbers, representable numbers. So if you have a real number lying in here, the ULP is just this distance here, which remains constant over the length of a binade. So in our analysis, we'll be using this ULP to actually bound the round-off error of any operation. So before we had some multiplication operation, and if we don't want to calculate exactly the round-off error, we can provide a sound upper bound by just saying it's going to be below the ULP of whatever that number would be. In particular, there are multiple rounding modes, but the one that's most common by far is round to nearest, which means round to the nearest number. So we can actually bound the round-off error by 1/2 of the ULP. While we focus on round and nearest in our paper and in this presentation, it's pretty straightforward to modify the analysis for another rounding mode if you want to use that for whatever crazy application you have. So I've gone over all this background. Does this actually matter in real life? We ran an experiment on a sign approximation to see how the error actually behaves. On the x-axis, we have the output of the sign approximation and on the y-axis, we have the absolute error, which is calculated as the difference between the approximation using a double precision format and a 200-bit precision format. We have a histogram here showing all the different data points, and you can see pretty clearly as we get closer to 0, where the step size or the ULP decreases, the round-off error actually gets much lower. And even nicer, we can see these very clear lines here, which are right on the binade boundaries. So as we cross that binade boundary, our round-off error gets much lower. So this is sort of the nature of the floating point numbers, which can be very complex as you get higher, as you have longer and more intricate programs. But clearly this has effect on the actual error that you see. And so our goal is to use this behavior to provide a nice error bound for the user. When doing static analysis, we know a possible range of values for a variable. And typically people will give a single error bound for that variable. However, this range of values can actually cross over a binade boundary. And we can utilize this fact to provide multiple error bounds for that variable depending on the binade boundary, which will allow us to tighten the error bound for these binades closer to 0. And so this is sort of the key idea of our paper, is that we can leverage these binade boundaries to not only get a more precise error bound, but we can also present to the user a better understanding of how the error will manifest in their program. I'll talk a little bit about our abstraction scheme now. So our abstract values are called segments, and we represent them as a tuple containing an interval, which is the range of values, interval containing the range of values that are possible for the variable, as well as a positive real number for the error bound. We write segments in a pretty standard way. But because we want to actually split and provide multiple error bounds across binade boundaries, we actually consider sets of these segments. And a set of a segment, if you really think about it, is just a step function, a piecewise constant step function. And so here's just a little diagram with 2 segments, one going from x to y with a certain error bound, and another going from y to z with a slightly higher error bound. So we'll abstract our floating point variables into a single segment step function. We form the interval by rounding the floating point number up and down, and we bound the error on that floating point number by just taking 1/2 of the ULP of it. The reason we have to provide an interval and an error bound here is because programmers don't always write exactly representable numbers in their programs. A good example is the 0.1 I was talking about earlier is a fairly reasonable number to write down in your program, but actually isn't exactly representable, and you're automatically incurring error when you write that. Once we do this, we'll have some segments, and we need to propagate the error through, and we do this by defining segment arithmetic. Segment arithmetic is just performing typical arithmetic operations over segments. So we have to find the new interval. We just do this using standard interval arithmetic, pretty well studied. And then we propagate the error using specific error functions for each operation. The error function has to take into account sources of error from 2 different places. The first is the existing error of the operands, colored here in red, and the second is rounding the result after it's been calculated, colored here in blue. So we can calculate the existing error, how the existing error propagates by taking the worst case values of the 2 intervals and seeing how that might propagate into the result. And then similarly for the rounding error, we take the potential result with the highest magnitude and we give that we throw that into the ULP function to understand the largest possible rounding error for our segment. We've defined some operators here for notational convenience, but they basically just take the result with the highest or lowest magnitude in your interval. This is really great, but the problem is we haven't actually split on the binades yet. So in order to handle this binade splitting, we have to modify our segment arithmetic slightly. The first thing that we do is we calculate the interval the result of the interval arithmetic to get the output interval of our result. And then we want to create a set of segments so that we can provide multiple error bounds. We will then calculate the error bound for each of these split intervals using a modified error function. Here we've modified the error function, and so it takes in addition, the interval that we're actually providing the error bound for, and then we just update our rounding error term to include the worst case scenario, so the largest magnitude. Because if you recall, as the magnitude gets larger, the ULP will increase. We have to include the original intervals as well for the error propagation terms here. And so that's why we end up splitting calculating the interval arithmetic first rather than along the way for each binade. There's a problem here, though, is that we've defined our segment arithmetic over individual segments, but the result of the segment arithmetic produces a set of segments. If you recall, a set of segments is really just a step function, and so we have to define arithmetic over step functions. So to do this, we perform segment arithmetic on each of the underlying each combination of the underlying segments in each step function. So here we just perform the arithmetic operation we've defined for segment arithmetic on each underlying segment, and then we need to perform a merge operation. The reason for this merge operation is that there's a possibility that these segments can overlap. So here we have an example where we're subtracting two step functions. The first has two segments, one going from 2 to 4 with some error bound, and the second one going from 4 to 8 with a different error bound. And then we're subtracting from that a single segment step function going from 1 to 3. When we perform this operation, we end up with two segments in our step function, one from -3 to 3, and the other from 1 to 7. And these intervals actually overlap on these segments overlap on the interval from 1 to 3. And so what this means is you actually have overlapping error bounds. So we have to find a way to ensure that these error bounds, we have to find a way to pick the appropriate error bound. We do this through the merge operation. The idea is pretty straightforward. You just want to pick the higher error bound for any overlapping interval. Here's a diagrammatic view of it. We've got two segments here, X colored in orange with a certain error bound, and Y colored in blue with another error bound. When we merge these two, we form the step function Z, which just truncates the segment with the lower error bound on the interval and the overlapping interval. This is sort of, now that we've done this, we're no longer chasing our tail, and we can perform arithmetic on segments, and we can propagate it through the program to find the error bound of our variables. We've implemented this abstract domain in a static analyzer. The users will supply some C code as well as input ranges for all the parameters. Here's an example of the C code with the sign approximation I was discussing earlier, as well as the input, how they might define the input ranges. From here we have X going from 0 to pi over 2. The analyzer will output the segments for all of the variables. To do this, we represent it as a CSV, where each row defines a variable called retval here, as well as a segment with a lower bound for the interval, upper bound for the interval, and then an error bound. And this CSV will give you all the information you need for your step function. We've run this analyzer on a selection of FP benchmarks, which is a standard floating point benchmark suite, and we compared it with the Fluctuat static analyzer. So we have a similar graph here to the one I showed earlier, where your output of your function is on the x-axis and the error is on the y-axis. We've added the error bound that Fluctuat gives as a straight orange line, and the error bounds given by our tool as these green lines. For the sign in the top left here, you can see that we improve upon the error bound for values closer to 0, and our analyzer produces an error bound that mimics the nature of the floating point error. As the floating point error experimentally seen goes down, so does the bound we've given for our analyzer. If we move on to the Doppler 1 benchmark, we see a similar pattern where we mimic the behavior of the floating point error and we improve upon the actual bound given by Fluctuat for certain subranges of the output. Rigid body 1, we don't actually improve upon the error bounds, but we do give the user a clearer picture of the behavior of the error in their program. So they can see where the error might be larger and where it might be lower, which is more information. Square root's an interesting case because the error actually proves to be flat. And so in this case, giving a single error bound produces a better result in all cases, but our step function analyzer will show you that the error bound is going to be flat without having to run costly experiments. One thing to note here is the number of segments we've listed here, and this will become important later when we talk about performance. It's particularly for the sine one, we end up with 4,167 segments. For certain programs, the number of segments actually produced for that variable is much lower, which is better for performance. Another benchmark we ran on that was pretty interesting is called CAV10. And this is interesting because it deals with branching. So there's another problem with floating point numbers and error that I haven't quite mentioned yet, which is known as branch instability. And the idea here is that if you are running your calculation using exact precision, then you might take one branch, but because of floating point error, you might go down another branch. And so this produces kind of an odd graph, right? You've got this split in the middle where you can see the two different branches, and you can provide error bounds for both of those. Fluctuat has a flag for you that allows you to say if you want to be sound in the presence of branch instability or not. If you do say that, then it'll give you a much higher error bound because branch instability will usually cause you to have a much higher error because you're executing different logic. If you don't, it'll give you a very nice error bound, but it's not sound in the presence of these errors. A nice part about the step functions is we can actually show how the branch instability changes depending on which branch you take. So on the left here, you can see that in the branch unstable case, we have a higher error, whereas in the other branch unstable case, if we were to go down the wrong path in the different case, then we'll have a lower error. Fluctuat only gives you the error bound for that top error. And so you can see how our tool gives once more insight into the actual nature of your floating point error. Branch instability was a little bit tricky to define the semantics for. I won't go into details of all this. It's kind of detailed. It's kind of intricate. But the basic idea is you have to determine if you have the possibility for branch instability and then compare the error for all stable and unstable paths. Talking about performance, our tool runs about an order of magnitude slower than Fluctuat, and this is because we're providing multiple error bounds rather than just a single error bound. In particular, step function arithmetic proves to be rather costly. Because we're performing operations for each segment in both of the step functions, the runtime grows with the size of both of those step functions. In addition, merging can be rather tricky as well. The tricky part is that you have to determine where these intervals overlap. And so we use a pretty naive implementation in our current code, but this could be improved using a more special purpose data structure. In conclusion, we think that taking into account binades will allow us to improve the error analysis in two ways. One is actually improving the error bound for certain ranges, and two is to give users a clearer picture of the nature of the floating point error in their program. There are some clear areas for future work. The first is that we didn't actually improve error bound in all cases, and the main part of that is that we were using intervals as the underlying value domain. Fluctuat uses zonotopes, and so if we define our value domain over zonotopes, then we could potentially potentially have our worst case error be the same as the error Fluctuat gave, or some other more accurate analyzer. There's some work to be done about how do you do binade splitting over a relational domain. That sounds pretty interesting. Another one is performance. Performance was slower, and the benchmarks that we were using was fairly small code. And so you can see if you have a much larger piece of code, this might take quite a while to run. The performance is directly impacted by the number of segments that were produced by our analyzer. And so one idea we've had is allow the user to control the number of segments. In particular, the amount of binades grows as you get closer to 0, but their size gets smaller. There's the same number of binades between 0 and 1 as there are between 1 and the max float. And so do users actually care about this level of fidelity near zero? Perhaps, perhaps not, but we can give them control over this, which will allow them to improve the performance at the loss of precision. And lastly, I didn't talk about the language features that we support for this abstract domain, but we support a limited subset of C, and we're missing a few key things. Functions is obvious, but loops is the one that I'm particularly interested in. I've taken a few stabs at defining widening and narrowing operators, but none of them have produced really nice results. Thank you. Any questions?
Let's see if this works. So questions? There's one here.
Yeah, thank you very much for the talk. So I may have missed that, but so you mentioned that one cool advantage of your technique is that you can provide more information to the users compared to Fluctuate. Like you have a stepwise functions that give you, even though they are not necessarily close to the error, they give some information on the shape of the error. Is this something that you can guarantee? Like, do you have some theoretical results on the fact that if your step function is higher somewhere, then the concrete error also follows this behavior?
Yeah, that's a good question. We don't have any theoretical results showing that the stepwise is going to necessarily mimic the error. And I actually think it's not necessarily going to mimic it exactly. So if you have, these are rather simple outputs to our error, right? But you can see with rigid body that things can get a little bit more complicated. Or even in the square root, we just have a flat error. So if you have a very complex floating point program, this error could have kind of very strange shapes. But I do believe that even if you have something kind of strangely looking and maybe even a little bit more continuous, then this will mimic the behavior better than this will mimic the behavior at some level.
Thank you.
Okay, another question, next question.
Am I right in thinking that for many analyses, the bounds are essentially like minus min double and positive max double? In other words, you have no idea. Like in your case, for the function on sine, you took in a parameter x. But you immediately said that the bound was down to pi over 2 or something like that. I didn't see that. Looking at the code, it looked like it would have just stayed as really, really large bounds. So.
Oh, yeah. Perhaps I misspoke. The users will have to input a bound on the parameter as it goes into the function. And so not that the output bound on the error, but they'll have to know at least on some level what could possibly be passed into their function. In order to provide a sound analysis on all different inputs.
Yes.
In which static analyzer did you implement the domain?
We have our own built static analyzer. Yeah. So we implemented all in OCaml using SIL for the parser.
Okay.
Potentially to integrate with Framacy down the line.
Okay.
Yeah.
Okay, good. Thank you.
More questions? So you discussed this interest of trying to bound the number of segments. Did you experiment with what would work well?
We haven't gotten that far yet. I think I ran some very preliminary experiments when I was running into long-running analysis. And in typical, I would just say if anything is below like 0.002, it's all the same segment. And that worked quite well. But there's more experiments will have to be done to understand, what might be a good way to bound it.
Okay. Right. If there are no more questions, then thanks a lot.
Yeah.
So next talk is about pointer domains.
All right, so thank you for the kind introduction. So here we go. So I'm going to be presenting C2PO, which is a weakly relational pointer domain. I don't know, is it my HDMI? It was working earlier. And we might need to use what? Okay.
Is that the only
It's the only HDMI, but I tested it earlier to avoid exactly this. But
No, no, it's just, it's not your fault. It's the thing.
let's see.
We have to do it.
Okay. Okay, I just need to set it up, but yes. Okay, so I guess let's start again. So thanks everybody for coming. I'll be presenting C2PO, which is a weakly relational pointer domain. This is mostly the work of Rebecca Guidini, who's a master student of ours who sadly couldn't be here, and also together with Julian Erhardt and Helmut Seidel. So let's maybe quickly take a look at numerical abstract domains. And there an observation that has been made for a long time is that you have basically extremes along this axis of precision, very precise but sort of slow, and on the other hand you have not very precise but very scalable. And for example, on this axis people often see intervals and polyhedra as the extremes, and then sometimes in the early 2000s a compromise was proposed there by Antoine Minet and others, and the key insight there was, okay, maybe I don't need to be fully relational, maybe I give up some of the precision, but then I still get something that is relational, but also scales meaningfully. And since then, a whole zoo of other weakly relational domains has been proposed, and generally there has been a lot of success there. And at some point we started wondering, okay, but why has this only been done for numerical domains so far? So we started wondering, maybe you can apply the same principle also where you only check pairs of the relationships between pairs of variables also to other domains. And our first paper in this line of work was some general construction to turn a relational domain into a weakly relational domain by some approximation. And we considered, for example, two disjunctive constants, and also considered a little bit domains that track strings, or in general conjunctions of inequalities between lattices. But then the other question also arose, okay, so for these you can do it, but what about, for example, the heap in C programs? So what about pointers in C-like languages? And there you also have the situation where you have techniques that are quite fast, but also very coarse. So if you think about tracking points to sets, potentially even flow and context insensitively, this tends to be very fast, but also very coarse. And on the other hand, you have techniques that are very precise and can give you very detailed information, such as shape analysis or things that are based on separation logic. However, there you also have to pay the price of this precision. So we started wondering whether we can maybe come up with some sort of compromise, and the compromise that we are proposing here is actually not C3PO, but C2PO. So the question is, why C2PO? And the idea here is that we have some earlier work on something that is called the two-pointer logic, and we were wondering whether one can turn this two-pointer logic into an abstract domain for C. And so it's the C plus the two-pointer logic. What we have in this two-pointer logic in general are conjunctions of mostly equalities between pointer expressions, where you have at most two variables in each of these equations. So what we did in this paper was we provided efficient approximation and implementation and experiments. And also we have extended this two-pointer logic with support for malloc, because in C you cannot do without dynamic memory allocation. And then the other thing that we found to be very important to add was some notion of disequality between memory blocks. So I'll go into that in a bit. Let's maybe first look at the two-pointer logic. So what might the formula there look like? So we have some formula here that has some equalities between pointer expressions. And in these equalities between pointer expression, you can also have dereferences and you can have offsets. So you see this here. So one type of information you can have. The other thing you can have is you can have disequalities. So here you would say, okay, Z is definitely different from the address of Y. And there also you can have in the disequalities, you can have dereferences and offsets once again. And then the last thing that we have added here are, as we've talked about, these disequalities between memory blocks. So this here would say that if you evaluate y at 5 and dereference it, then you will be in a different block than the block that x is in. So a little bit more formal. What does this logic look like? Well, for the terms, you have, first of all, the address constants. Then we allow ourselves a set of registers. So basically, you can think of these as any sort of variable in C that never has its address taken. So it cannot be modified by some assignment to some place. We can directly see when it's modified because it's only modified directly. And then we also allow dereferencing, and there we allow some arbitrary offset C for dereferencing. Then we have some writing conventions that make it easier to write things. So if we dereference something at an offset of 0, then we just leave out the offset, makes it nicer to write it down. And also for variables, if we dereference the address of the variable x, we just write x. That just makes the formulas a little easier to understand. Then our atomic propositions, they look like this. So you either have equalities between terms with an offset, or you have disequalities between terms, once again with an offset. And then lastly, what's new in this work here are these block disequalities. And the idea behind block disequalities is the following. If you have standard compliant C, then you can do address arithmetic, but you can never leave what the C standard calls an object with this address arithmetic. So if you have a variable x and a variable y, you cannot use address arithmetic to go between the two of them. Because yeah, basically you need to always stay within the same block. And then one of these block disequalities basically says, okay, there is no offset z such that you can add it and go from one to the other. And then our formulas are simply conjunctions of these atomic propositions that we've seen. Now for the equalities and disequalities, I guess it's sort of easy to imagine where they come from. For the block disequalities, it's maybe useful to say once again that for all variables, we have the block disequalities. And also when we do a malloc, C guarantees us that we basically get a fresh block of memory. So we can also say that all of the mallocs, all of the blocks that we have allocated will be in different blocks. Now with these equalities, what happens is if you have a bunch of equalities, you basically get other equalities from them. So if you have two equalities, you get potentially a third and potentially many more. So for example, if you know that x is equal to y, and you know that y is equal to this dereference expression here, then you can infer, okay, x is actually equal to this longer expression here. And you have the same situation with equalities and disequalities. So if you have an equality and a disequality, then you can also infer basically here in this case that x is also not equal to this longer expression here. And you have a lot of these inference rules where basically a lot of equalities and disequalities are implied. And it is even so that usually you have infinitely many equalities that are implied. So for example, if you have an equality that x equals y, then you can keep dereferencing on either side, and this is still an equality that will be implied. So what we need actually is a nice and compact way to represent all of this information. And there our proposal is to, instead of directly considering these formulas, we consider something that we call a kernel representation, which is this nice 5-tuple here. So I will explain what we have here. So first we have a set of terms that we are talking about in this abstract value. And here this is a set of terms is supposed to be subterm closed. And it is supposed to contain at least all of the terms that our original formula psi also had here. Then for the equalities, we represent it with something that we call the quantitative congruence closure. So you have this pi and the omega, and this is a compact representation of the equalities. We'll see how exactly it works in a second. And then for the block disequalities, we now only store block disequalities between the representatives of the classes in this congruence closure, and we also do the same for this normal disequalities. Now this quantitative congruence closure, what do we mean? Well, we mean a congruence closure, but the elements that you have in there that are equivalent to each other, it means that they basically can be reached with a constant offset. And then what you have obtained is you have obtained a representation that is unique for a given set of terms, provided that you have fixed some total order on the terms such that you can always pick the smallest term as the representative. So what does this look like? Let's consider some formula psi here, and I have marked the equality in orange. And we have picked the set of terms to be the address of x, the address of y, our temporary a, and x and y. And then in pi, we basically have the different congruence classes. So the address of x and the address of y are in their own thing, the same for y. However, a and x are put into the same class because we have here that there's a constant offset between a and x, namely this offset 2. And then in the omega for all of the elements in each of the classes, we basically write down what is the offset from the representative. For the single element ones, this is very easy, it's always 0. And then here for this x, the offset is 2, because in our term order we have decided that these auxiliaries are smaller than the variables. So this is our quantitative congruence closure. And we have implemented this with a quantitative version of the union find data structure. And you can find more details on this in the paper if you're interested. Now for this formula, we have talked about how we represent the equalities. However, there's still the disequalities to go. So what do we do for disequalities to get the complete kernel representation? Well, block disequalities, we don't have any, so this is easy. And then the disequalities, we once again store them only about the representatives of the congruence classes. And here A happens to be the representative and Y is also the representative. So we can just store it as this 3-tuple here. Okay, so now we have how we represent our abstract values. The next question is we need to define the lattice operations on those. And the first one that we give here is the meet operation. And there you say if you have a two non-bottom abstract values, K1 and K2, then to define the meet, we first extend the set of terms for both such that they are equal. And then we step by step add the propositions from K2 into this abstract value for K1. And this is a convenient way to define it because we already need to provide transfer functions for all of the guards anyway later on. And so basically we can do the meet here in terms of adding single propositions. Then what does the partial order look like? Well, for our partial order here, we make use of the meet that we have just defined, and we say that K1 is smaller or equal to K2, if and only if meeting K1 and K2 together gives you K1 again. So this equivalence that we have defined here, or if two values are equivalent according to this order, then this implies the semantic equivalence. However, it is not precise, so the other way around does not hold. So if two kernels K1 and K2 are semantically equivalent, but one of them talks about a larger set of terms, then the one that talks about the larger set of terms will be truly smaller than the other one. So this is a drawback that we have here with this definition of the partial order. Then the next question is, what do we do for joins? And if we were in the formula world, everything would be very easy. Because in the formula world, you just say, okay, the join is the OR. However, the OR is sadly not in our class of formulas. So then the next idea would be, okay, how about I consider all implied equalities? However, there's also a result by Gulvani, Tiwari, and Nekula from 20 years ago that it is not always possible to represent all of these implied equalities as a finite conjunction. So this is also a problem. However, here we have nicely sidestepped this problem because we are not talking about the formulas, but we are talking about our kernels. And for our kernels, we have a fixed set of terms that we talk about. And so this is no longer an issue here. And we simply consider only the intersection of the terms. And then for the equalities, the join actually is the least upper bound that we have here. And for block disequalities, we need to do a little bit of work because after the join, some equivalence classes may be split and the representative may change. But there I would also point you to the paper for details. Now for the join, we have only talked about the equalities. Now what about the disequalities? Actually, there we once again have a bit of a problem. Namely, if we consider two formulas, psi 1 and psi 2 here, and one time we have A is equal to 2 plus X, and the other time we have A is equal to 3 plus X, then both actually imply that A is unequal to Z plus X for any Z that is not 2 or 3. So basically, we have now here obtained a cofinite set of disequalities between A and X. And there, once again, we have this problem that we do not have a best finite abstraction for it. So what we do, or what we have to admit, sadly, is in the presence of the disequalities, our join actually remains an over-approximation. The advantage of the definition that we have done for the join is that actually in this setting, if you apply the join repeatedly, then your sequence of values will become ultimately stable. So basically we can use our join as a widening. And still, when we are not widening, if you want to get some of the precision back, what we can do is we can basically grow the term sets of the argument to the join before we apply the join. So what this means is that the values, the concretization remains the same if you grow the term set for one of these things, but the abstract value becomes smaller in the lattice order. So if you are careful, you can basically do this to avoid being too imprecise when you do the joins. And yeah, you can preserve some additional information. The other question, we've talked about widening, so immediately the question arises, okay, what about narrowing? And actually here we have the situation that we have infinite descending chains of kernels. So we need to do some engineering. And basically here the solution is we somehow need to bound the magnitude of the appearing constants. And for the details there, I would once again direct you towards the paper. Okay, so we have defined our lattice, we have defined the operation on it, so now we actually want to do some assignments with it. And first of all, let's consider what we do when we have an assignment to an unknown expression. For example, we assign T1 to question mark, and then what you need to do is you need to forget the information about all terms that may be modified, and that is all terms that may have the same address as T1. If T1 is an atom, then it is as an auxiliary, then it's not really a problem, because you know that nothing has the same address as this auxiliary. You can simply remove all formulas that basically talk about A, and then you're done. If it's actually an expression where a pointer dereference happens, then the situation is a lot more complicated, because then you can keep only equalities or disequalities about the terms where you can actually prove that these two things will never be the same. And this can either be the case because you know from the normal disequalities that it will never be the same, or you know that the things are in two different blocks and they can also never be the same. And in these cases, it is basically crucial to know that these memory cells are not the memory cells that the write is actually looking for. What we can do when we implement this in a static analyzer, though, we can do a little bit of a Jedi mind trick. Namely, we can additionally also use some information that maybe a non-relational heap analysis has computed and provide this as an additional input to this transfer function to say, okay, you do not have the block disequalities or normal disequalities for these two things, but we can assure you that they will never be equal. Now, when we assign something a bit more difficult, a bit more complicated, then the general procedure is very similar. We only make use of these auxiliaries here to make our lives a little bit easier. So basically, we add a fresh auxiliary, then we add an equality between the right-hand side and the auxiliary. Then we remove all of the terms that are potentially modified by the assignment, as we have seen before. Then we add an equality back, and then lastly, we remove the auxiliary again. This is a little bit of a trick to make it easier. Okay, then I promised I would talk a little bit about dynamic memory allocation. So what do we do if we have something like this? So we have T1 is equal to call to malloc. Well, first of all, everything that potentially modified by this assignment needs to be removed, as we did before. And then for all of the terms that are appearing anywhere in our equalities, disequalities, everything, we can basically add this new block, this equality, that the block of all of these things will be different from the block that we have just newly allocated. Because intuitively, nothing will be in the same block that we just got from malloc. All right, so we have actually also implemented this domain within Goblin, which is an abstract interpreter for real-world multi-threaded C programs based on side-effecting constraint systems. And we have experimented to get a feeling of the precision of the domain. We have experimented with the core util programs. And what we did is we basically generated invariants with C2PO and then instrumented the programs with these invariants. And then we compare three different configurations of this Goblin tool. Namely, we consider a basic configuration where we only have a non-relational pointer analysis. Then we consider a var-eq analysis, which tracks more general must equalities. And then we considered our C2PO domain. So in total, we generated about 20,000 assertions for these programs. And luckily, C2PO was able to verify its own assertions. Everything else would have been depressing. But what's also interesting is this other relational analysis, VAR-IQ, was only able to show about 8,000 of these assertions. And if you go to a non-relational analysis, then it's only about a fifth of the things that can be shown. So this seems to be some evidence that the C2PO domain actually computes some interesting invariants that are out of reach for these non-relational analysis. Now the other thing always is, well, how does it perform, this entire thing? For this, we have considered a larger set of benchmarks, namely we have considered all of the soft verification competition, the reachability category, and we have basically plotted the runtime of this base, so this is this non-relational analysis, versus the runtime of the C2PO. And you see the runtime of base on the x-axis and the runtime of C2PO on the y-axis. And basically what this means is for all of the data points that are below this diagonal base was slower, and for all of them that are above the diagonal C2PO was slower. So we can see that in general, we actually observe a little bit of a slowdown, but it seems the slowdown is not too bad. So it's usually below a factor of 3. So this is the 95th percentile value. And we consider this to be quite good, to have a slowdown of 3, but being somewhat relational. And then there's also these cases where we're actually faster, and this may be because we have basically identified key parts of the program that are actually not reached by being relational, and then sometimes being more precise can even be faster. The other thing that's maybe a bit sad that we have to say here, it did not significantly change the number of correct verdicts on these SVCOM tasks. So these tasks, they come annotated with some goal that is to be proven, and often this is quite an intricate goal, and apparently we got more precise, but quite often we're still not precise enough to prove this invariant that the SVCOM wanted proven. All right, so to quickly wrap up what we have done, we have proposed this novel domain C2PO to track equalities and disequalities between pairs of pointer expressions. We have seen that the block disequalities are crucial for handling assignments. And we have also done some preliminary experiments in Goblin that look sort of promising. And with this, I'd like to thank you for your attention, and I look forward to your questions.
So, anybody has got a question for Michael? Yeah.
What do you do in situations where a pointer might point to two different mallocs, maybe as a result of a merge or join?
So if the pointer may point to two different mallocs, then you sometimes need to get rid of the block disequalities. Then you cannot maintain them anymore. But it's something that can happen and happens quite regularly. If you think about some sort of branching and then you join again, then it may be two different mallocs, yeah.
Okay. You?
Yeah, so I have a question about the disequalities and how you represent the set of all disequalities. Because when you allocate a fresh block using malloc,
yep,
then you become different from all the other blocks.
Yes.
So do you represent all the disequalities one by one, or do you have a set of mutually exclusive set like you do in separation logic to have a shorter version of?
So those we don't actually represent explicitly. So the Goblin analyzer for these malloc blocks, basically it creates new variables, and then we basically have this implicit information that the blocks for variables are always disjoint.
So you have names for different IDs, and if the different IDs for different blocks, and if the IDs are different, then
yeah,
okay.
Yeah.
Thanks.
So it's only for unified presentation here, because otherwise you get into these problems of how to best represent. And there, this was the easy way out. Let's put it like this.
Okay. More questions? So you said that you were not quite there with respect to the SVComp benchmarks. Would C3PO help you?
I mean, C3PO is very smart, so maybe yes. Realistically, the problem of some of these tasks is that they come from the model checking community. So they are sometimes annotated with invariants that are very hard for abstract interpreters to prove. So you would need to do a lot of loop unrolling and such things.
Right.
So I don't know if C3PO might help solve more things, but I don't think.
I mean, would it make sense to have 3 PO with the pointer? I mean,
okay. Yes.
Yeah, no, I'm not.
Whether having 3 pointers would actually help.
So
Yeah, I'm not.
would that make any sense? I'm not sure that it would.
So I think it might be interesting to do it, because a situation where you might actually want to have 3 pointers is if you think about offsets into arrays, for example. So then you could have, okay, I have an equality between some variable and then the kth element of this array. And then you would have a 3-pointer expression. Whether this would go a long way towards the SVCOM task, I cannot say. But in general, it might be an interesting generalization of this thing here.
Yeah. Other questions? Otherwise, thank you.
Thanks. Do you also want her thing? Or?
I hope not.
Okay, then you can give it to me back.
On stability.
Hopefully it stays like this. Or maybe not. Yeah, so what I'll be talking today is a new abstract domain that tries to track the trends of numerical variables and how they evolve during the execution of a program. As you can see, there's a bunch of people in this work, but at the core, there's really the master thesis of Sophia. So all the props for this work goes to her, and apparently I might need a dongle as well. Let's see. As I was saying, all the props to her. Anything that you don't like, it's on me, so don't blame her. Okay, so we're talking obviously about numerical domains. You have a plethora of them to choose from, depending on how complex the properties that you want to prove are and how much you're willing to pay in terms of performance for proving those properties. The basic choice, mostly for teaching and proof of concepts, are domains like signs, parity, or constant propagations. They are fairly quick, and they can prove numerical properties in very simple settings. Like here, if you just read something, and if that something is greater than 10, you perform a division. Knowing just the sign of the variable x is enough to prove that there's no division by 0. But if you change the program slightly by just adding some computation on the divisor, the sign domain is not enough anymore. So you have to switch to something a bit more elaborate that can still be non-relational. Oh, sorry, I forgot. Can still be non-relational, but that now allows you to perform some computations and some reasoning over some arithmetic expressions. Two of the most common domains are the intervals and the congruences, and just by switching to intervals, you're able to detract 1 from x and gaining an abstract value that is enough to prove that there's no division by 0 there. But you can still produce very small programs that that make the intervals domain go become completely useless. In this case, there's just an iteration over an array, and we try to print every element of the array. So you know that the length of the array is positive, but you don't really know how long the array is. And you know that the element you use for the access is positive, but you don't have any relation between the two. So one smart thing that you could do is try to combine intervals with something else, and you get the pentagons domain. Or you can move to something completely different and start to track complex relations between variables, and you get to proper relational domains. So you can sort of draw a line here, and you can argue whether pentagons should be above or below that line. But that line partitions these, the set of numerical domains into roughly two words. One that is rough in terms of precision, that works with simple properties, but it's really, really fast. And one that is instead able to prove a lot more complex properties, but it requires some computational effort. And so the work that I'm presenting is kind of lies in the middle, more towards the left side, but it's still something that is that we strive to define as our non-relational domain, because we want to keep the fast performances, but we still want to be able to express some relational properties between variables, and we also would like to have, as an addition with respect to the non-numerical domains that are usually used, we want to be able to tell something about values that are statically unknown, so like user inputs. Starting with an example, here there's just a small solidity smart contract. The fact that it's something that runs on a blockchain is completely coincidental. You can look at whatever other programs, but this contract has a set of accounts that hold money inside them. And there's a function set that transfers a certain amount of money from the owner of the, from the sender of the message to someone else. And you just have a couple of preconditions. You ensure that the amount is positive and that it's actually available on the account of the sender. And if those are true, you take out the money from the sender and you pass it to the recipient of the transaction. So what we would like to show here is that obviously only one account can increase and only one account can decrease, which seems pretty straightforward. But the problem here is that all of the numerical quantities going around here are statically unknown. The amount of money in the balances keeps changing from one transaction to the next one, and the amount is really user provided. So there's no way of knowing what values these variables will take. So this is a no-go for any non-relational domain. Every amount is top. Every quantity, is top. You can refine, for instance, with intervals, you can say, okay, this is not really top, this is anything above 0. But when you take that out of something that you know anything about, you still go to top. And with relational analysis, you might learn something in these specific case, depending on the choice of the domain that you have. But even if you take polyhedra, it's easy to put some nonlinear increment here if you're not talking about money, and you get a rough approximation as well, and you'll need to move to a different domain, and so on. So the idea that we had to kind of be able to provide some intuition of what this code is doing without having to pay the price for those highly costly relational analysis is that we might, instead of talking about the values of the variables, we might want to to speak about how they evolve during the execution of the program. So for instance, regardless of the concrete values that they might take during the program, if we know that what is subtracted here is positive, we can is positive, you can for sure say that the amount of money of the sender has decreased. It doesn't matter what actual values they are, you know that this is true. And the same goes for the amount of money for the recipient. If amount is positive, then the money he has available will be increased. And even from this high-level intuition, you see that we're not really talking about the values of each variable. Now, the fact that here there's a variable and we take it as the only thing that needs to be positive is just coincidental. You don't have any expression in here. It's not tailored to a specific, for instance, linear increases or decreases. Doesn't matter as long as you can compute, in this case, the sign of the expression that is here, you will be able to say something about the left-hand side of the assignment. But the downside is that you must be able to say something about those values. In this case, it's only the sign. You might require some more information, like the fact that it's exactly one value or that it falls inside a range of values and so on. And the stability abstract domain tries to infer these kind of properties. We defined it by first defining a small lattice of per variable numerical trends. So in here you see that this has the same shape of an extended sign domain, the one where you have the 0 or plus, 0 or negative. And in here you have elements to say that a variable is decreasing strictly or not, it's increasing strictly or not, it stays at the same value, or it changes, but you don't know if it got bigger or smaller. And once you have this lattice, you can just lift it to program variables. All the lattice operators are just pointwise applications of the operators from the trend lattice. And what's important here is that whenever you look at an instance of the stability abstract domain, what it's saying is how the values of each variable has changed with respect to the previous instruction. We're not tracking anything globally inside the program. We just want to know how every instruction changes the values with respect to what it was before. So let's see an example. This is the same code from before. The analysis will start by saying that every variable is stable. You don't change the values by entering a function. The two prerequisites here are just no op. Whenever you traverse a condition, you don't modify anything, any value of any variable, so everything just stays stable. And then after the first decrement, you see that all of the variables are still stable, except the left-hand side of the decrement that has now become decreasing. And when you move to the next instruction, the previous left-hand side becomes stable again because it's not modified by this instruction, but now the balance of the recipient of the transaction has increased. So as you can see, these are just relations with respect to the entry state of the computation and not global with respect to the beginning of the function or the beginning of the program. But we want to say something about the whole function or the whole program. So when you're done with this analysis, when you have a stability instance for every program point, you can just chain them. You can look at sequences of instruction and combine different instances one by one. And the way in which you combine them is just by combine the trends of every single variable by just looking at this table. If you have a variable that increased and then was stable, then overall it has increased. While instead, if it increased and then it decreased, you go to top, because we're not dealing with the values, so it might have gone back to the initial value, it might have gone lower or still higher, so you don't know, you just go to top. And when you have this chained information on sequences of instruction, you can merge them over different paths after if the analysis or at loop exits by just using the list upper bound. So it's very straightforward and not really costly. So if we go back to the example from before, the chain from here to here will just be no op because everything is stable after every instruction. The first change here is after the first decrement, when the only thing that changes is on this variable here that pass from stable to decreasing, so overall it decreased with respect to the previous value. And then when you chain another instruction, as you can see this time, the first variable is still decreasing because with respect to the beginning it went down, and you just update the second variable. Pretty straightforward. Now, I've kind of overlooked how we decide that something is increasing or decreasing. Specifically, I briefly spoke in the first example that you might need, you do need information on the amount that you're detracting from a variable, but you also need some information whenever you reset the value of a variable to a different value. Because if you perform this assignment, the variable increases or decreases depending on its previous value. So you do need some information on that as well. And we thought of this need, let's say, as our analysis needing an oracle, so something that it can query. And it turns out that there's a kind of product that exactly falls into this category, and this is the open product. So whenever you define the semantics of an instruction, you define it in terms of abstract queries to this auxiliary domain A, and you just stop at the first query that yields true. So you start, if the first query returns false, you pass to the second. If this returns false, you pass to the third, the fourth, the fifth, and the first one that returns true is the one that determines the stability of the value after the assignment. Practical note, open product is nice for the formalism, but whenever you implement this, you can just use a pre-analysis. So even if this auxiliary domain is very expensive, you're not required to run it in combination with stability. You can just run it as a pre-analysis without incurring in extra costs, and then you can just query whatever you computed before. A couple of examples of how we define the semantics. Here you have an assignment to X that increases its value by 3 times Y. And let's say that we use the sign domain as auxiliary domain in our open product. And if you try to compute the result of this new assignment by just using the sign information, you have something negative plus something that is 0 or positive, and the result will be top. So you're not actually able to say anything about the result of this assignment. But if you look at stability, and you can have any value here, I just put something random. The first thing that you do is you reset anything to stable, because every variable that is not explicitly assigned here will go back to stable. And then you begin your series of queries to the sign domain. So you start by asking if the expression you're adding is positive, you can say it. If it's negative, if it's exactly equal to 0. And the first query that returns true is if this expression is greater or equal than 0. And that corresponds to the non-strictly increase. So you're able to determine the stability of variable X in this way. As I was saying, the query go on after that in our definition. So we organize the queries in a less and less restrictive way so that the first 3 queries aim at determining strict increases or decreases. And if you're not able to say anything strictly, you move to these other queries that also apply equality with 0 so that you can have non-strictly variations. And if all of them return false, you just go to top. Let's see another example. This time we use a multiplication, which is a bit harder to handle. This time the query to the sign domain are a bit different. And specifically, we query both something about the variable that we are updating and also to the expression, but this time the expression is compared with 1 and not 0. So 1 is a problematic element for the sign domain because it lies in the middle of the plus abstract element, so you're not able to tell whether an element is exactly 1. So what happens is that all of the queries that we have return false. And so we end up going to top, losing all of the information. So what you do in this case, you just swap out the sign domain with a more expressive domain, and interval here is enough to recover all of the precision for the stability abstract domain. And specifically, you're able, I just handpicked this value to make the example work, but you're able to say that X is always negative before the assignment, and that the value of Y plus 2 is always greater than 1. So you are able to say that the value of X will strictly decrease. And one thing to notice here is that, well, I also forgot it, sorry, from the previous example. So let me go back a bit. One thing to notice here is that when the auxiliary domain goes to top, you can sometimes recover some information. So you get something more out of your original analysis by using stability. And the second takeaway from these examples, let me find it, okay, is if you do the computations with intervals, you have an overlap between this element and this one. So you're not really sure what happened to X. But if you pair this information with stability that tells you that the value decreased, you can kind of cut off possible combinations of X before and after the assignment to refine your knowledge about what happened to X. So this was kind of the end of the master thesis from Sofia. We had an implementation inside the Lisa static analyzer working on the imp language that Lisa uses for testing, so nothing practical and nothing that we can extensively test. And the next step, so what you will see now is just a bunch of future works, is to understand where we want to apply it and where there's space to apply this domain. The first area, as I was saying from the smart contract thought before, is to kind of try to prove some functional requirements of the program, like the fact that one account decreases and one account increases. And while doing this, you can also obtain some relational information between variables, and specifically which variables are covariant, so they increase or decrease together, and which ones are contravariant. So when one increases, the other one decreases. This is really just a byproduct of chaining the stability information. So when you get to the end, you already can partition the set of variables by their stability value, and you can quickly see that the two balances here are contravariant, and so you could prove potentially the non-functional requirement. Sorry, the functional requirement. But this is a bit messy, because if you want to evaluate this, you will have to run this analysis on a set of programs, and every program will have its own functional requirements, so it's something pretty hard to verify automatically. A second possible application that we basically found out while writing the paper is that you can, in some cases, in specific cases, you can use this analysis to prove termination of loops. So you would start by just running the standard stability analysis. Here I left out the state from the auxiliary domain just for clarity. You will start by saying that everything is stable, then you go inside the loop, you propagate, you see that one variable increases, the next one decreases. You go back and you perform the least upper bound between the two states, and then you go outside of the loop and there's no modification to the variables. Now, instead of chaining the stability information to the end of the function, you would chain it to the end of the loops. And if you're lucky, in some circumstances, you have loop guards that are contradicted, let's say, by the chained stability information that you have at the end of the loop. So in this case, you know that you go inside the loop only if X is positive, and you know that after every iteration of the loop, X will decrease. So you can somewhat, in some situations, show that a loop will end. You don't know anything about the number of steps that it will take, but you might get lucky and be able to say that it terminates. But the probably most promising, at least in the eyes of the supervisor of Sofia, application of stability was trying to understand if the error arising from floating point computation is stable or not. So if you have a variable X that contains some floating point, you can kind of track the floating point error associated to the value of X with some ghost variable. And if you look at what happens, more or less, I don't want to upset you. I know you've worked on this. This will be very profane, so please bear with me. If you look at what happens during the evolution of this ghost variable along the program execution, you'll see that there might be some operations that are applied to X that doesn't change the actual error, but then you can have something more, some new operation that make the error become bigger, and then maybe somehow you manage to reduce it, and then you go on until you reach the end of the program. And if you track the stability of this error throughout the execution of the program, and you try to chain the information, you basically go to top anytime. You know that these errors can become, even tiny variation of this error can cause increases or decreases, and when you have two of them with opposing sign, you just go to top. So the idea that we have, but we haven't tried it at all, is to, instead of exact stability, we would like to track stability up to a sliding tolerance window that is centered around rho, that in the example that I'm about to make is exactly here, and has a breadth of epsilon. So what happens with respect to the plain definition of stability is that whenever the modifications to the error stay inside the sliding window, you deem them as stable. You can go on, and then at some point when you find an update to the error that brings the value outside of your sliding window, you say that the error increased, and you adjust the sliding window to the new value. So after that, you can start again by saying that that's stable and stable, and whenever it goes out again from that window, you update the window, and you keep going with the analysis. So the intuition that we have is that you can look at places, at portions of the code that you are analyzing and say, okay, the error inside this loop or inside this if is stable up to epsilon, but you can also change the information over the whole function, and now you're no longer going to top, but you can say that the error overall increased because you had this jump and you had to adjust the window. Okay, so just to recap, we have presented and defined a new abstract domain that is that relates the values of the same variables at different program points inside the function or the program. We are able to express sometimes information about variables that the other non-relational domain are not able to infer anything on. And we do keep the nature of non-relational domains to be fast and to scale relatively well. But this is really still a work in progress, so as I was saying, we have a number of directions to go on. We're not sure if they will work. We'll try them, and then I'll let you know. But after deciding this, we really need to go down to the benchmark, because even the fact that we are combining the domain with another numerical domains might make it not that scalable, especially if the domain is something like the octagons or the polyhedra, so that we need to assess what impact this combination has with respect to the plane analysis with just the numerical domain. And as you saw in the example from the floating point error computations, the semantics of stability is not really decided yet. Depending on the application that we have, we might need to tweak the semantics a bit, so we don't really have soundness proof at the moment. So that's also a big area to work on. Thank you.
Any comments? Yeah, Katrina.
So I have one observation and one question. So regarding the termination thing, you have to be very careful, because just knowing that the variable is decreasing doesn't guarantee that a loop terminates, because it may be decreasing a little smaller every loop, and that doesn't give you termination. So you have to guarantee that it decreases by a certain amount. So like at least 1 or something, if you have integers, for instance, or I don't know, for reals, whatever. Just decreasing is not enough, so be careful with that application if you're looking into that. The question then was regarding, so you have this oracle thing that is a sort of a pre-analysis. Is it not worth it having it as a sort of a reduced product kind of thing?
The formalization is an open product because actually we didn't see, at least for what we saw right now, the need to refine stability with, to refine the auxiliary domain with the stability information. At least not in the few programs that we analyzed. So that's why we settled with the open product. And the other reason for this is that the fact that you're defining your abstract semantics using queries doesn't really bind stability to work on a specific domain or a specific set of domain that are able to support some kind of operations. You're just querying them, and so that made the definition a bit more flexible, in our opinion.
Okay, thanks.
Okay, thanks for the talk. So you have a question on nonlinear assignments and queries. So you mentioned that the property you're looking for, sometime even polyhedra may not be enough to get it because it has issues with nonlinear assignment. And then you showed us a linear assignment and how you deal with it by doing queries to other domains. How do you generate those queries? Is it handcrafted, or do you have a general way to?
No, so what we say, let me go back with these that are a bit faster. So like, take this example. We don't really, so the queries that we have are not dependent on the expressions that came here. What we identify is that there's a variable that appears also on the right-hand side, and that is multiplied by something. And we don't care about the structure of that something. The queries that we have is we take that something, we put it inside an equality with 1, and we pass them to the other domain. So it's up to the auxiliary domain to be able to say something about that expression.
Okay. But how do you decide which query you need to do? Like here, you do it for the multiplication. So you have okay, you have something for multiplication, and then you deal with other kind of expressions.
Yeah, so we have one for the assignment to what we call an independent assignment, so an expression where x doesn't appear here, so like the assignment to a constant or whatever. And then we have all of these kind of expressions where x is multiplied by something, is added to something, is you take out something with a subtraction, with a division, with a power, or these are the kinds of updates we support up to now, at least. Yeah.
Okay, thanks.
Oh, just to conclude, and every one of these operations have different queries. So we have made a list of what in our eyes, but again, we don't have soundness, so we're not sure those are correct, but what in our eyes are the conditions to say that a variable is increasing or decreasing with respect to either value of a variable or the expression that happens outside. So every operation has its own queries, and we just plug the expression in and send it to the other domain. There's one there.
Oh, right, yes. A moment. 3-0 to this side.
So I have a thought about an application, which is automatic inversion. So
Sorry?
automatic inversion.
Okay.
So if a function's monotone, or like, then it's 1-to-1, and it can be inverted, right? So the thought was maybe you could use an analysis like this to say when you can provide an automated inverse. And this has showed up in a couple different projects I've worked on. One is when you're trying to do a change of variables. So whenever you have something in variational inference or in computer graphics, you'll often do some sort of change of variables, and there it's useful to have an inverse to perform that. And then also when you're doing like sparse computations, it's often useful to have an inverse map for the sparsity pattern in your computation. So I don't know, the question that I have is maybe, do you think this is related, or does it make sense?
It might. I think we'll need to chat about it a bit before understanding if it is, but definitely, I'll come back you in a bit.
Okay. More questions? I had a quick thought, maybe a little bit related to that. Here you're running your analysis forwards, as far as I could see. Would it make any sense to look backwards and see if I want this to be increasing? What are the preconditions for this?
It might. Again, the biggest driver for us to make the analysis forward were this idea from Agostino Cortesi to tackle the floating point error with this sliding window, and that was a bit why we went with the forward analysis. I think if there's an application that might be tackled with a backward analysis, then maybe yes. I think it's driven by the objective of by the properties that you want to prove.
Okay. Right. There are no other questions, then thank you very much, Luca.
NSAD today. And the first talk today is going to be on work in progress, label union find for constraint factorization by Mathieu Lemaire and Dorian Desprez.
Yeah, thanks for the introduction. So this is a work in progress paper with my PhD student Dorian. And so what is this talk about? It's about a new family of very cheap relational abstract domain. So earlier, Michael did a nice introduction to the topic where you have non-relational domains which are very inexpensive, and you have these expensive domains like polyhedra, which are very expensive, but you have lots of relation. And in the middle, you have these weakly relational abstract domains which are less expensive, but you have fewer relations. But actually, they are still very expensive because you have a quadratic costs in storage and cubic costs in computing some operations. And so we want a cheaper abstract domain that doesn't need all these mitigation strategies, things like that. So the idea is to have a very cheap domain which is still relational, so it can be always on, and you don't need to worry about having it in your base abstraction. And so what this relational domain can do is to compute binary relations between variables. And it can compute relations like y equals a times x plus b, so affine relations, or with relations like y equals x XOR some constants, or with some constant rotation, or even with some permutation. Actually, any kind of invertible relation, a relation expressive as an invertible function, will be representable in our domain. So we think there are two main applications of this domain. The first is natural, is to increase the precision of your abstraction by having more relations between variables than if you had just a non-relational domain. And the second application is what we call constraint factorization. Is the idea of you can make existing domains more efficient by grouping variables together, and the idea is that you will have fewer variables in your abstract domains, and that way your abstract domain will be more efficient. So this was a summary. Now I want to explain why are these weakly relational domains. They are already very costly, and I think one of the main problems is an operation which is called constraint propagation or reduction. So the idea of constraint propagation is to improve the precision of your abstract domain without having to change the concretization, the set of values that it represents. So I will be using as an instance the zone abstract domain, so relation of the types y minus x is in some interval, and I will be representing them as a pair of variables mapping to some abstraction of relation. So here I will be using an interval. So for each pair of variable, I'm using an interval. So for instance, this represents that between x and y, you have the interval 1 or 2. So one kind of constraint propagation can you apply? The first is apply reflexive closure. So you know that the relation between x and x is always 0. So you can refine your abstraction thanks to this knowledge. The second one is symmetry. So if you know that y minus x is between 1 and 2, then x minus 1 is between minus 2 and minus 1. And so you can propagate like this. The operation done for this is the inverse of the relation. In the case of intervals, it will be just the negation. And the last operation that you can use is transitivity. So if you know that y minus x is between 1 and 2, if you know that z minus 1 is between 3 and 5, then you know that z minus x is between 4 and 7. Okay, so if we look at what we get here, what is the storage cost of all this is quadratic in the number of variables. So if I have 3 variables, I need at least 9 relations between all 3 variables. And the computation cost is basically the transitive closure of a relation. It is cubic. So those are actually very expensive. And the worst is that you always have to do this full constraint propagation. So you always have to do a transitive closure before joining. And this is a general result in abstract interpretation. If you don't do that, you will lose precision. So you cannot avoid doing this constraint propagation. So the idea that we get is, okay, maybe we can make the domain more efficient by doing the contrary of constraint propagation, which we'll be calling constraint elimination. So the idea is that we want to remove some relations if it can be efficiently recovered by constraint propagation. So, for instance, we can do reflexive constraint elimination. So you don't actually need to store the relation between y and y because you will not be able to have something more precise than the 0,0 interval. So you don't need to store this information. It is implicit in your set of constraints. You don't need to store both the relation between y and z and the relation between z and y. You can infer one from the other. So actually, you can divide the cost by 2 by storing only one of those two relations. It works particularly well because the negation of intervals is an exact operation in the sense of a forward complete operation. The real problem is elimination of transitive constraints. So if you wanted to remove the relation between x and y, you could do that, but it means that you would have to compute all the possible paths between x and y, compute what is the relation on each of these paths, then do the intersection of all these values, and then take the best one, and then you could do that every time you wanted to know the value between x and y. So obviously it will be very, very expensive, and you don't want to do that. So that's why we will be cheating here, and we will be using an assumption. And the assumption is that the value that you will be computing on every pass will already be the same. So if you have this assumption, then you don't need to compute the value of on every pass. You only need to compute the value on one path. And so basically, all you need now is that all of your variables are linked to the other. So you only need a spanning tree of the graph to store the set of relations. And now if you want to store to compute the relation between x and z, then it's very easy. You just have to compute this relation between x and y, and then the relation between z and y, and compose that. So this becomes now very inexpensive. So this explains how our abstract domain works. So now it will not work for the zone abstract domain because the zone abstract domain with intervals on relations doesn't have this property. But if you restrict the zone abstract domain to have only constant offsets between two pairs of variables, like this, then it will work. So for instance, if you know that the relation between x and y is plus 2, and between y and z is plus 3, then you know that the relation between x and z is minus 1. So this is the general idea of what our domain computes. And to implement that, we will be using a data structure which we call label union find data structure. So as you saw here, basically the set of relations represent a tree. It will be a rooted tree, so a tree where each element points to its parent. And we will be using that. But before, I want to say that the natural settings in which this restriction that I propose, the fact that the value on every path is the same, it will naturally form a group structure. So for instance, you will have the law of associativity, because if I have this diagram here with many relations, then basically if I go from this path to x to z, then followed by t, or if I do this one followed by this, those must be equals. And if you look at that, it implies that the composition association is associative. You will also have neutral elements because the path from x to y is the same from the path from x to y to z to y. And so the composition between L2 and S3 will be a right neutral element for the composition here. And you have neutral elements, but you also have inverse elements, because if this is a neutral element and this is a neutral element, then basically L2 is the inverse of L3. So associativity, neutral elements, and inverse elements mean that we have a group structure. So this brings me to this label union-find data structure. So it's actually a union-find data structure. So if you don't know what union-find is, it's just a tree where every node is pointing to its parent. But the difference is that on this link from each element to its parent, we will have a label like this. And we ask that all the labels obey the group properties. So we need an identity relation on labels, and the possibility of inversion of every label, the possibility of composing any pair of labels. And we want all these operations to obey a loop of group. And we have three main operations which are derived from the union-find operation. So the first is find. So basically, we take an element n, and we want to find both the representative element, which is the root of the tree, but also the relation that you have between this element and the root. So the relation here will be the composition between two from LM, then LR. And moreover, we'll be updating the tree. This is an operation which is called path compression to make a shorter link from the element to the root. Another operation is the add relation operation, which corresponds to the union is a union find. So the idea is that if we say that we learn that there is a relation between n and m, and this relation has label L, then we will be adding a new relation between the roots. So we compute the root of n, which is Rn, the root of m, which is Rm, and we add this link, which is basically inverse of Ln, then L, that Lm, between Rn and Rm. And the last relation, the last operation that we need is get relation. So if we want to know if n and m are related, then we compute the root of n, the root of m, and if they are equal, we know that the relation between n and m is ln followed by the inverse of lm. So all those operations are very efficient. The union-find data structure is one of the most efficient data structure in computer science. It's all operations are almost equal, are almost constant. Now we did some study of what does it mean for an abstract relation to be a group. So basically, there is something that we want for our abstract relation is that all the operations are sound. So the abstract composition is an sound abstraction of the concrete composition of relations. Same for inversion and same for identity. And basically what we found is if you have both the fact that your abstract relations are sound and that they follow the group laws, then it means that all relations must be injective function. So for instance, the zone constraint here is not an injective function, because if I precisely know the value of x, and I know that y is x plus some value in some intervals, then I cannot deduce the value of y. So it's not an injective function. Whereas if I have just the relation y equals x plus b, then if I know the value of x, I will retrieve the value of y, and vice versa. So this is an injective function, and that means that it can be encoded in our abstract domain. Another interesting property. So actually, I said it was injective function. It's actually injective function between equivalence classes. So it means that you can actually take some information about variable x, some information about y. If you can relate both of this information using injective transformation, then you can also encode it in our domain. And another interesting property is that if you don't do anything stupid, your lattice will be flat. So basically, either you will have no relation, you have bottom, so incompatible relations, or you don't know the relation between two variables, or the relation will be precisely one invertible function. So once you know that, it's also the contrary. Whenever you have an invertible function, you can encode it in our domain. So we thought, oh, what can we use as a relation in our domain? So one very useful relation is this affine equality, so two variables pair equality. so of the form y equals ax plus c. So this kind of relation happens a lot in our programs, of course. An interesting case is affine relations in modular arithmetics. So if you multiply by 2 in modular arithmetics, it's basically equivalent to doing a shift. So it means that you are losing some information, which is information about the top bits of the old value. So this is not an injective function, so you cannot represent it in our domain. But if you take an odd number, because an odd number will be primed with 2 power something, then it means that it can be represented in our domain. So we can represent ax plus b in modular arithmetics, but only if a is an odd variable. Another interesting property is to take, so if you do a XOR with a constant, then it can be reverted if you XOR again with the same constant. So this is an invertible operation. If you do some kind of rotation, it's also an invertible transformation. So it's also possible. Actually, if you do any kind of permutation, you can encode it in our domain. And if you look at it very closely, the combination of XOR and rotation means that you can also encode shifts if you know what are the values of the bits that have been shifted. So it seems weird, but actually there are lots of cases where we can use this relation. And yeah, there are many other relations that we could think of. Okay, so now I've explained all the kind of relations that we can encode using these new abstract domains. And I want to explain some of the applications that we have been starting to study. And one is a reduced product with a standard and SSA-based non-relational domain. So I will first explain what is an SSA-based non-relational domain. It's something that we published this year at PLDI. So basically, we have an analysis which builds a set of terms, which we call symbolic expressions. And our numerical state is a mapping from each symbolic expression to some interval. So for instance, we know that variable x has value corresponds to the term alpha 2 plus 7, and alpha 2 plus 7 is mapped to this interval between 7 and 11. And we show that if you do that, you are always more precise than a standard non-numerical domain. And why it's more precise? Because it's actually not really non-relational. You actually have some relations between your variables, and the relations are given by the relations that you have between all the terms. So what we can do is to apply some constraint propagation between all of the subterms. For instance, if we know that this condition is true, it means that this variable is below 11, which implies that alpha 2 plus 7 is below 10, which implies that alpha 2 is below 3, which implies that 2 times alpha 2 is smaller than 6. So this works well. So how can the label union find domains that I've presented be useful in this context? Well, the first thing that we could think of is that you will be able to find new relations that we could not represent before. So for instance, we can represent a relation between alpha 1 and alpha 2. Say, okay, maybe we know that alpha 1 is 3 times alpha 2 plus 2. And so we can propagate more information, because if we know that alpha 2 is in this interval, it means that this alpha 1 is in this interval. So we learn something, we are more precise. But another interesting application is what we call constraint factorization. So the idea is to say, okay, actually all of these variables are grouped using this label union find data structure. It means that normal union find are used to represent equivalence class. So we have some kind of extension of a notion of equivalence class, and where all the variables that are related, we can group them. And instead of storing the interval for each of these terms, we represent only an interval for the representative element of the term. And it's interesting because when we do constraint factorization, instead of studying all the possible relations that you have between any pairs of the variables here, we update the interval for the root once, and then all of the other relations are automatically updated. And so we save a lot of time spent doing this constraint propagation. So there are some conditions for this to work. And the condition is that the operation that is represented here, the injective transformation, must be forward complete with regard to the non-relational abstraction. So +7 is complete compared to the interval abstraction here. So this works well. So yeah, to conclude, this is where we are currently. What we have done, we have defined this new kind of data structure, the labeled union find. So maybe it's not completely new because you said something that may be similar, this quantitative union find. It will be interesting to find out the relations between both. So what is this label union find? Is a union find where you have labels which are elements of a group. We have a new family of abstract domains, which is based on this labeled union find data structure, using abstract relations as labels. And as we saw, it can represent many injective functions between equivalence classes. And we saw that there are two kinds of use cases. The first is to use the domain as is, just to increase precision of non-relational domain. So if you have only non-relational domain, it will be very useful. But if you have relational domains, when we think that this domain can still be useful as a way of having fewer domains, because you can group domains together to have fewer variables. So for instance, if you have octagons and you have this constant offset domain, then instead of representing the relation between x, y, and z, then maybe you know that y equals x plus in some constant, and you can remove y from the octagon representation. And the difficulty then is that you have to be careful when you do the join, because you have to do this constraint propagation on the fly, which makes the algorithm a bit more complicated. So I think there are a variety of applications of this domain, not only in abstract interpretation, but also in constraint propagation or in decision procedure. This could be useful as a cheap way of representing some information. But of course, in abstract interpretation, it's harder because we have this join operation, and actually just joining the union find is quite complicated. So we will be interested in exploring this constraint factorization in a variety of domains, because it could work for octagons, polyhedra, linear equalities, two variable par inequality, things like that. Because a subset of the domains can be represented by our labeled union find domain. And we are working on a robust open source implementation on our codex analyzer. And we want to do some benchmark and evaluation before having a full paper. So thanks for your attention, and I will be happy to take any question.
Are there questions for Mathieu?
Thanks for your talk. Have you looked into actual sort of C code examples? I'm imagining when you have all these different abstract domains, you can get really sophisticated like analysis of integers. Are there like some examples that motivated this? Because it seems like when I think how a lot of people write these, the programs are often not that complex. So, but maybe happy to be proven wrong here.
There are many examples where it can be useful. For instance, if you have often you have some like a while loop where you increment a counter and you also increment in sync a pointer. So you will have a relation between the pointer offset and the counter. And so this is exactly the kind of relation that you will be able to represent here. So a relation between the two of these variables. For now, we have already checked that it does not make the analysis complexity more go higher. So it's cheap, and in some cases it gains precision. But actually, to fully take advantage of this, we need to be very careful in the way that we do our reduced products between the non-relational domain and in this domain. And this is not fully as fully precise as we would want. So we gained already some precision in some case, but yeah, we don't have the full numbers for that yet, so that's why it's still work in progress.
All right, I think we have time for one or two more questions. Okay, then maybe I have one. So you've said you have already experimented at least a little bit with it, and you said the overhead is at least not huge. Do you see an overhead at all, or is it sort of so cheap or that it basically pays for itself?
Yeah, I think from what we saw, it was less than 10% overhead, so
Okay.
very, very, very cheap. Something that I did not mention is so we are in these particular settings of this SSC-based analysis. So what you have here is that the relation between different terms is flow insensitive, and because it's flow insensitive, you can represent it in a union find, which is the imperative union find, the standard one when you can do path compression and things like that. This is what we have implemented yet. But we would also like to have some flow-sensitive labeled union find data structure. But for this, we need to implement a join algorithm, and the algorithm is a bit more involved. And this is something that we don't have yet. So, yeah, we don't know for that. Probably we'll have more precision gain when we have this flow-sensitive union find, but we don't have it yet.
All right, thanks. And then one last question right here.
So thank you for your talk. So how it compares with the e-graphs which are used in SMT solving and so on? Because you have these nodes where you apply a function and so on. So you try to generalize to some properties about symbolic computation on these graphs and so on. But could you explode more such structures in a symbolic way?
So e-graph is basically you have this subterm relationship, and then you have equalities, but you also have to perform the congruence closure. So we don't have this congruence closure, but our notion of equivalence is stronger because we have this injective function in the middle. So I think both are complementary, and actually it would be very interesting for us. It's something that we would like to go to, is to use also e-graphs instead of just terms in our abstract domain. But I think they are related but complementary. Yeah.
All right, then let's thank Mathieu one more time.
Yeah, thank you.
And I guess we are now, for the last but certainly not least talk of this session, moving into the world of quantum computation once again. And Nicola is going to tell us about abstracting entanglement, and it's this one here, which is joint work with Alessandra Di Piero and Isabella Mastroeni. Katharina, I think we might need the magic adapter.
No, I think you can see me. Okay, nice. Hi to everybody. And so in this work we try to abstract the quantum entanglement. So before starting with the abstract domain part of the talk, what is entanglement? But first, what is a qubit? You know that since you are in quantum computation, the smallest information unit usually is a qubit. That, from our point of view, the only thing that we have to know is that in general, this qubit could be represented with a two-dimensional vector, with a vector in a two-dimensional Hilbert space. And so, since we have in a two-dimensional Hilbert space, we need two bases that usually are 0 and 1, so these two vectors. And since we are in a Hilbert space, it's a complex space, so we need two complex number, and our state will be the linear combination between the two bases. And this is how we can represent a qubit. But the entanglement is a phenomenon that happens when we are working with more than one qubit. So let's see how we represent system which there are more than one qubit. Let's consider, for example, 2 qubit. 2 qubit, the state of 2 qubit states in a space that it can be made composing the space of the single qubit. So in this case, we have 2 qubit, we have the space of the 2 single qubit, and we put together the space using the tensor product. So in this way, we obtain a 4-dimensional Hilbert space. So we have 4 bases, and the state of these 2 qubit will be a linear combination of these bases. So a 4-dimensional vectors. Similar, if we have 3 qubit, we will have the composition via tensor product of the 3 spaces. So 8 dimension, 8 bases, and the vector will be a 8-dimension vector that corresponds to a linear combination of the 8 bases. So you see that when we want to obtain a bigger space, we compose the smaller space that composes the bigger one using the tensor product. So for example, if we have these 2 qubit, their state is a state in a space that can be obtained composing these 2 single states, but the global state can be expressed in this way. So if you have 2 qubit, can we express the state of these 2 qubit composing, using the tensor product, the single state of the qubit? The answer is sometimes. In particular, when this happens, it means that these 2 qubit are separable. So basically, the state of the first qubit and the second qubit are independent. So the global state is a composition of the 2 single states. This is just like a classical state in which if we have 5 bit, the state of this 5 bit is the composition of the 5 single state. When we cannot write the state in this way, it means that the 2 qubit form basically a unique state. So this means that the state of the system, that in this case is composed by 2 qubit, cannot be described separately. Because basically these 2 qubit that can be 2 particles, 2 quantum particles, basically their state are linked, so entangled, and they cannot be separated. But what does this means? Let's see first with some example. For example, if you have this state, it's 2 qubit that form this state, so a uniform superposition of the 4 bases. We can actually write this state using the tensor product. So this is the state of the first qubit, this is the state of the second qubit. In fact, this state corresponds to a state in which the 2 qubits are separable. In fact, if, for example, we do some operation to the first qubit, just like a measurement, we can obtain different results since the first qubit is in superposition, but in both cases, the second qubit is still 0 plus 1. In fact, you see basically when you measure 0, it's like we select this part of the state. When the measurement returns 0, it's like we choose that this part remain. Of course, it's a probabilistic things, but we can say that basically this part of the state remain, and you see that here is 0 plus 1, the second one. Similar in the other case, the first result 1, so we keep only this part of the state, and the second is still 0 plus 1. The things are different if we consider an entangled state. This is an entangled state. How we can see that? We can see that. First, we can see that we cannot separate the state of these 2 qubit, because basically we cannot say that the first qubit is 0 plus 1 as before, because basically the first qubit is 0 only when the second is 0, and similar with the 1 case. In fact, we cannot write this state using the tensor product as a composition of 2 states. In fact, if we measure the first qubit, again we have 2 possible results, but if the measurement returns 0, we have basically choose the first part of the state. So also the second is 0. The same happens when this one. And this happens when we do a measurement, but can happen also with other operation. For example, if you have this state, we apply the Z operation, that is a simple operation that changes the sign of the amplitude of 1. So if you have alpha plus beta, it's become alpha minus beta. We obtain this state in which we have changed the sign of the first, but we have also changed the sign of the second. So since these two qubits are entangled, it's like they form a unique state. So every time we work on one of the two qubits, we are actually working on the pair, because they are not separable anymore. For this reason, it's important to reason about entanglement, because if you think about a quantum program in which we have quantum variable and some variable are entanglement, if you write Z Q0, we are working on Q0, but we are also altering all the other variables that are entangled with Q0. So it's important to understand which are the group of entangled variables in order to proper model which are the variables that are altered every time that we do some operation. So what we want in our domain, we want that if we have some qubit in some state, we want some abstract representation that work on the set of qubit and told us which are the set of qubit that are potentially entangled. So for example, if in this case, we know that every time we work on Q0, we also alter Q1, and every time that we work on Q4, we do not alter the other one, for example. And this is what we want to obtain with our abstract domain. So first, we need to define some property. The first property that we define is the separability that we already seen before. We generalize this property. We see before the separability with the case of two qubit. In general, if we have a set of qubit and two qubit that stay in this set, we say that these two qubit are separable if basically we can break the state in two states where, for example, X is here and Y is here. Okay? And when this doesn't happen, we say that these two qubits are inseparable. In this case, we don't speak of entanglement, but we speak about inseparability, because when we have two qubits, being not separable is the same as being entanglement. When we work in a multi-qubit system, it's a bit more complicated, because the entanglement in a multi-qubit system not only looks to the global situation, that's what we are looking here, but it also looks to the single binary, to all the relations that are in the subsystem, basically, so which are the relation between the pair, between the group of three, and so on. So for this reason, we use the word inseparable to refer to the concept that we don't want to model all the possible relation in the subset, but only understand if we can divide or not two variables. There are more detail about this in the paper. So, for example, if you have this state that we can write in this way, it means that we can separate one from the rest of the state. So this means that D is separable from A, B, C, but A, B are not separable, like B with C and C with A. So how we represent this, the separability or inseparability of this state, using a partition on the global of the set of the qubits. So in this case, A, B, C are together since they are not separable, and D is in another set because it's separable from the other one. Here there are some other examples. For example, in this case, we can separate A and B from CD, so we can represent the state in this way. And similar in the other case, we can represent the separability in this other way. So apparently, we have obtained what we want, because given a state, we have the set of qubits that are separable. But is this enough to proper reasoning about entanglement? Let's see this example. In this case, we have two entangled states with two qubits. We note that this state is not the one that we have seen before, because basically there are a minus sign, And this minus makes this state entanglement, while in the previous case we have a plus, so we can write in this way. In this way we cannot write this state as a composition of two separate states, because there is a relative phase here, that is the minus sign, that don't allow us to break the state. So these two states are entangled, and from the separability point of view they are the same state. Like in the abstract domain, they are the same state, since A and B are not separable. But let's see what happens if we apply a measurement to these two states. For example, if you measure the first qubit, in the first case, we can obtain 0, 1, of course, because it is in superposition. And in the first case, the second qubit, according to the result of the measurement, may be 0 plus 1 if we measure 0, because we choose these two if we measure 0, or 0 minus 1, because we choose these other two. So, if we measure A, we alter B, because B will be one of them with a different relative phase, but B is still in superposition. In the other case, if we measure A, like we have seen before, the B will be 0 or 1, but you see that in this case, B will collapse to a classical state, because basically this is always 0 or always 1. So this is a quantum state, but it is in real classical, because there is no superposition of value here. Instead, here we have a superposition of value. So you see that the relation between A and B in this state and in that other state is different. Because when we do a measurement, basically when we do a measurement here, we causes more damage, because we make also the other qubit collapse to a classical state. And why this is interesting? This property is interesting because imply another things that happen when we apply a control knot operation, that is a knot. So we negate B if A is 1. And if we apply this operation to the first one, we obtain another entangled state. Because basically we do nothing here. In this case, this is 1, so this becomes 1. We do nothing here, this becomes 0. In fact, this is 1, 1, and this is 1, 0. Instead, in the second case, if we apply C naught AB, we obtain this state. Because in this case, we do nothing. In this case, we negate B, so it's become 1, 0. So you see that in this case, when there is this direct relation between the qubit, with a simple operation, that is a C naught, it's a simple gate, we have this, we have nullified entanglement between the qubit. So this is why this strongest link that happen in this case is important for our domain, because thanks to this, because if we are able to track this property, when we are also able to understand when some operation can nullify the entanglement. And this is why representing only the separability, it's not enough. But we need also to represent this other property to get more precision. So we define this property as a direct inseparability because it's like a direct link between the qubit. And basically we say that two qubits are directly inseparable if when we measure one, also the other collapse to the base state, as we have seen here. As we have seen here. So, for example, if you take the first part of the state of the previous example, we can apply different measurement, and you see that if you measure A, we can obtain two results in which you see that here C is in superposition, is 0 plus 1, but B is always 0 or always 1. The same if you measure B, A is always, okay, this is a typo, should be 0. A is always 0 or always 1. Instead, if you measure C, A and B are in superposition. So with this example, we also see that this property is also transitive, because if we measure A, B collapses to a base state. If we measure B, A collapses to a base state. And so in this case, we obtain that the direct inseparability in this state happen between A and B, but not with C. So if we want, so we know that I and B are the inseparable, and if you want to represent this property, also in this case we may use a partition of the set of qubit. So this say that the qubit that are in the same set are the ones that are the inseparable. And here we can see with the C0 that if we make a C0 between two qubits in the same set, we nullify the entanglement. Instead, if we do with two qubits in different set, we basically obtain another entangled state. So, given a quantum state, what we want to represent is the separability, in this case A, B, C, and D, because there is a tensor product, and the direct inseparability. In this case, since to be direct inseparability, you must be entangled, so you must be inseparable. D is separable from the other, so it's still not the inseparable with nothing. And the three state ABC, the three qubit ABC, that here are all together. If we consider the direct inseparability, as we've seen before, we have A and B that are direct inseparable, and C that is not direct inseparable with them. So to represent these two partitions together, we use this notation, which basically represents the smaller one, that is the direct inseparability, and we add some index to know which are the sets to join to obtain the set of separable qubit. So more formally, our abstract state will be a set of pair where the first element is a subset of the qubit and the second element is an index, and in particular all the first set together must form a partition of the original set of the qubit. And we use this letter to indicate the domain, that is the set is a subset of the set of the pair between subset and the pair of subset and the integer. So to complete the domain, we need to define an order in this domain. In particular, with this order, we want to represent the fact that we need to overestimate the inseparability, since our goal is saying which are the variables that may be entangled. So in this order, we overestimate the entanglement. But at the same time, we need to underestimate the direct inseparability, because being direct inseparable implies some effect. So if we want to be sound, when we apply this effect, we need to underestimate this relation. So this inseparability must be ordered in this way, and the direct inseparability in the inverse sense. And the final order, basically we can define the order in which we respect these both directions. So you see that when we go up, the set of inseparable variable become larger. You see that here there is always 0, so it corresponds to this set if we join the 0. But the single set that correspond to direct inseparability are smaller. So concluding, now we have the abstract domain with an order in it. We have the concrete domain that, in this case, in our case, is made by sets of vector in the Hilbert space of the qubit. We have defined a concretization function that goes from the abstract domain to the concrete one. In particular, this concretization function build the set of the state in which we can separate the state according to the bigger partition, and in which all the qubits that are inseparable are actually inseparable in the state. So I mean, this means that we build the concretization correspond to all the states that are properly abstracted by the abstract state. And then, since these two relations, the inseparability and separability relation, are actually an equivalence relation, because they are both transitive, symmetric, and reflexive, we have a since they are equivalence relation, we know that we can build a Galois connection between these two domains. We have the concretization function, and we can use the concretization function to define the abstraction function. If you there are more detail in the paper about the construction of these two functions. And so concluding, what we have done with this domain is we have introduced a domain that allows us to reason about entanglement. In particular, our goal was to bring in this domain enough information to capture when the entanglement may be nullified. So in this case, as we have seen before, if we simply represent the entanglement, we cannot say if an operation nullified the entanglement, but if we add the information of the direct inseparability, we know when an operation like a CNOT nullified the entanglement. So in this case, with the richer domain, we know that with this operation we pass from the state in which A and B are inseparable and direct inseparable to the state in which A and B are separable. And we have built a domain in order to build an analysis, in fact, as a continuation of this work that was a future work in the paper, but now is more an actual work. We build a static analysis that fully employ this domain. So basically, we have added also another element to this domain that it is some label to represent the state of the qubit, and then we have defined all the abstract semantics to properly analyze the entanglement. Thank you.
Are there questions for Nicolas?
Okay, just trying to understand precisely. So it's not closed under simplifications, right? So you might have two Hadamard gates after each other that correspond to the identity. And if you analyze the first system, you would get that they are entangled, if I understand.
Yeah, I mean, with the Hadamard gate, you cannot. I mean, with the Hadamard gate, you create the superposition. Like with basically, the idea is we want to track when there are some gates that might nullify the entanglement. Of course, with some approximation, because basically everything is reversible, but you cannot actually represent everything. So this is the idea. I mean, I have a slide with a sort of an example. Okay, this is an example. To actually complete the analysis, you also need some label. This is come from the paper, so we use also this simple label that come from another previous work, in which basically, let's say, the value of the qubit is classical in superposition plus top and bottom. So the idea is there if you simply use a partition, so you simply represent the relation of separability. Here you create a superposition. With the CNOT you create the Bell state, and you arrive here, you don't know anymore. You don't know nothing. But with the indirect inseparability information, you basically have this adding information, so you know that these are entangled, but there are also direct inseparability. So if you add another CNOT, you are able to know that now P is a classical value, so it's separable from the other. That is the idea. Okay, in this case it's easy because you apply it to CNOT, so they nullify by themselves, but it works, I mean, it depends on the circuit, but it works also with more complex example. But it's not more like the understanding, it's more like abstracting the state than understanding if there are like specular operations that nullify by themselves.
Any further questions?
Yeah, so you don't have a static analyzer yet, but maybe you already tried to see if your abstract domain works well of standard quantum program gates, and how you did this kind of studies thing. How accurately can you represent some quantum gates with this abstraction?
Yes, we are defining a static analysis now, and yeah, basically we add more label here because we need more label to add more position, and yeah, what we have done, we have taken for now the set of minimal gate, so Adamard the gate. The set of Clifford gates, so Adamard, Clifford gate plus T, so Adamard, C naught, T and S, and we have built the abstract semantic of this 4 gate, that is there enough to represent all the computation, and yeah, in order to have the abstract semantics on the domain, in order to do static analysis, the classical way, we can say, like do the abstract execution of the program and obtaining this information in every point of the program and then use it.
So if there's any urgent last questions, I think we would have time for one more. But I guess not, so then let's thank Nicola again. And that's already the last talk, but before people run away, first of all, Michele and Vincenzo are going to say a couple of words.
Thanks, Michael. So, NSAD 2024 ends here. Thank you all for attending. We hope you enjoyed the event. And thanks to all speakers for the nice, very nice talks. And thanks to all reviewers, of course. Some of them are here. Thank you for your hard work during the review process. And thanks also to ACM Sigplan for supporting us and for publishing the proceedings. Of course, thanks to Splash for hosting us. And we hope to see you next year at Splash 2025 in Singapore. Maybe there will be another NSAD. And okay, that's it. We have maybe one last.
Yeah, I'm not able to share my screen, but just my final remark. So I want to sponsor this Zulip group we built after. Okay, yeah, the magic adapter. Oh, okay. When did you mention the magic? Let's use the magic adapter. Better. Yeah. Let's try. Let's see. Maybe it's my. Yes. Oh, give me 1 second, please. Or we can do. Okay. Okay. So a couple of weeks ago, after the Lipari Summer School on apps interpretation, okay, some of you were there. We decided to create this Zulip server about apps interpretation. Okay, some of the people are already there. We are almost 100 people there, and we decided to build this Zulip server about apps interpretation to keep our community, okay, the community about apps interpretation, connected all together. So this is the link. So if you want to join this Zulip group, I would be very happy. Okay, and yeah, just this final remark about this Zulip group. So please join the server, and that's all for this edition. So we will see next year in Singapore. Or I hope so. Hopefully. Hopefully. Thank you.